Okay, anything else?
Okay. All right.
All right, thank you so much for joining us again. We appreciate that. And we have Passaic County Technical Institute on, and they is an entire class that is
Right.
working on the lunar table. So, and
Is this the habitat table or the work table?
so I call the lunar table the habitat. I call the work table on my schedule.
Okay, that's fine.
So that's how I differentiate. Okay, sorry. Introduce yourselves. Go.
Hi, I'm Maya.
I'm Zach.
My name is Ben.
Tell 'em about the table. So it's actually a work table, not the lunar table.
Oh, okay. That's great. So you were listening to what we were saying just now?
Yes.
Oh, awesome. So I'm going to change it to work table. Okay. Is it all right if I record this?
Yes, that's fine.
Yes, it's fine.
Thank you, Maya. Okay. Oh, I see you have a prototype there.
Yeah. Yeah.
All right, we're ready.
Okay. So our work table first is it has a handle that is made of pipe cleaners and duct tape. So basically our table has a latch on it. This latch just closes the table in half so it can fit in more spaces and be smaller and easier to carry. So when I take the latch off, we have our legs here. So our legs, we're trying to do more so of a telescoping leg so that you can expand it to 3 different levels, depending on if you want the table to more so sit on your lap or be higher up. So I'll show you how that works. Like this. It's kind of like.
So the leg extends into 3 separate pieces, and at the top here, this is like a little clip, but this is supposed to represent a spike. So that way, when you're out on like the lunar surface, you can like kind of stab the table into the ground, so that way it doesn't really like move anywhere. And this cap will be so that you don't really like stab yourself or anybody else when it comes to transporting this thing. Or if you have like an area that doesn't really need a spike, you can just put the cap on and have it sit there. And then it also has like a hinge at the bottom here. So that way, once you collapse it, it folds down with the cap on. So that way, so it makes it easier to carry once you fold the table back in together. And so we have 2 outlets on this side. We don't know what type of outlets they use, so we just use the like American ones as just like a placeholder. And then here by the handle, you're gonna have a little cutout for where the 4 meters of cord is gonna sit in. And it's gonna be on like a rotating strip that you can easily like pull and pull back in. You want to go for it?
So for the drawer, for the extra space, we put it inside so that it can easily expand out so that when there's more storage or there's available tubes, they can put it right in there instead of having to go back to the shuttle, which wastes more time. For the legs, for the ideal materials used when this is final, we would like for PFTE, Teflon and titanium, usually titanium for the spike so that when it's on the ground, it'll stay on there. And then for the cap, we'll use Teflon. You want to?
It's all in, then you just fold it up. So this is how it's gonna be folded up, so that way it's just gonna be easier to like bring on and bring off. And then for lighting on the table, we have one of those like gooseneck lamps. So right here will be like the lamp cover. So you take off the cover and then you pull out the gooseneck lamp and then put the cover back on. And the reason we have the lamp cover is so that way no dust and debris gets in the little the pocket for the lamp while they're doing any construction on the table.
So we can show you it's standing just on the one leg because it's not. Ben, no.
No.
We're not extending it. We're just keeping it down just to show you.
Got it. All right. And that's how it
Yes.
would be like, standing up.
Yeah, and then when, of course, with the telescoping legs with the 3 buttons, it'll be able to expand all the way up and close down. And the buttons will also be bigger, so it's easier to push it in.
Okay.
I love that you made this out of things you had readily available. That is so cool. I think that is really awesome. And when you didn't have something, you made a picture, which is or a spot. That is really cool. And this is the first one that I've seen that folds up like a suitcase. I mean, you got the model of a suitcase, but I will let the reviewers take it over. Thank you, though.
Gene, David, you guys want to start?
I would like to say, this is one of those things, and I love your prototype. The fact that it's the first one that started out that way. But one of the things it's bringing to mind here for me is our recent visit when Dave and I were down looking at the rovers, and right next door to us was the astronaut training just to how to bend over to pick up the shovel and things like that. And I'm picturing in my head while they're opening this up, that astronaut and how much problem they had just with bending over and picking up a shovel. And I love your demo so much because I'm looking at that going, how can that be done by an astronaut out there? And the fact that you're the first team that get to that point and make me think this says a lot about your work you've done. Great job. I like everything you've got here set up. Especially the spikes in the bottom that emerge from inside. I think when you go to make a prototype, a life size prototype for the critical design review, think about if you're in New Jersey, so you're not used to bundling up like that kid in Christmas Story. He's basically, I can't move my arms. You know that kid. Have somebody like that with big old gloves, double gloves, hockey gloves, trying to open up and do that. That's what you have to picture in your head. Your model is very well done. I like everything you've got in there, but picture that when you go to build the next prototype. Dave?
Yeah, first of all, I apologize. I came on a few minutes late, so I didn't hear the beginning of this. I'm just going to say what the others do. I am incredibly impressed by the fact that you've built something, right? It's one thing to have this all drawn out on paper, but you've already got a basic idea here that you're building on. I'm interested in knowing what materials you're thinking of recommending for the actual flight hardware of this. And I apologize if you already said that. Like I said, I came on a couple of minutes late. So when you take this to the next level, you guys are going to use some type of material, and I'd like to know that. But I'm also interested in finding out what research you've done and what you're thinking about this as a final prototype. If this were going to the moon, what would it be made of?
So for the flight, we're still researching on the material because we haven't found one yet. But
Okay.
for the Teflon and the PFT and the titanium, they're all able to withstand the constraints of the temperatures, so
Good.
they won't erode your dust. But this would be the ideal materials, at least for the spikes, the telescopic legs, and then for the actual table itself, those would be the ideal materials for that.
Okay, so and tell me a little bit more about those spikes, because I'm really intrigued by that. What will be the mechanism that drives those down into the soil? Is there going to be a spring, or is this going to be done manually?
It's gonna be done manually.
Okay. And I think that's good because, it's like anything else. Lunar soil is not going to be different in many respects to what we have here on Earth. Sometimes you kind of, it's like if you're digging in a garden, sometimes you push a shovel down and you're just going into fairly soft dirt, and other times it's pretty rocky. I think if you're just using the normal force that you would by, applying your foot or whatever, you're not going to get this jammed down so badly that it's going to get stuck. And then you're going to have to really work to try and get this thing back out. When you get to that point, think about how you can do that, right? Maybe just take this thing outside. Now, wintertime, ground can get a little colder, so maybe you can create something inside to simulate how you want to have this done. But I'm just going to echo what Gene said. When you get this done, just put on like some heavy duty gloves, right? And think about how easy it is to manipulate this without the freedom of having, your fingers flexible and everything else. Even something, a latch or whatever that would hold this together. Think about the fact that it's going to have to be big enough that someone can manipulate this easily, wearing not, again, we say big, heavy gloves here, that you're simulating the fact that a spacesuit is pressurized, right? And so everything is stiff. You don't have the kind of flexibility that we take for granted. Mm-hmm. So you want to create a situation where you're as close to what an astronaut is going to have to deal with. But again, we've been looking at a lot of presentations, and I'm always impressed with any group that has taken on the task of starting to build. Because it's only once you get this, in 3D and you're manipulating it with your hands that you begin to understand how it's going to work and what the challenges are going to be. So keep up the work. I'm very impressed.
Thank you. Okay, so you understand that they're going to have big gloves on, so your handle even is going to have to be way bigger than what it normally is. Your plugs have to be able to resist dust. And also another thing that Glenn mentioned just this morning was see if you can find some kind of plug. We don't know what kind of plug it is. We want you to research it and find it, but maybe that it wouldn't unplug easily if somebody tripped on the wire or something. So the dust and the big hands and the gloves and the astronaut being able to bend are real important things when you're designing this. And one other thing I would like to mention is no sharp corners or edges. So just round everything off.
Okay.
And one more thing. You see how you have the caps on the spikes? If you have something like that, make it tethered, because we don't want the astronaut losing any part of it. So just if there's a cap, tether it so it could be tethered or untethered if you want, but make it tethered so that we don't lose everything. I love that it fits in a suitcase. Everything is together. If there's any moving parts, make sure they are tethered onto that also, because that way we won't lose anything on the moon. Go ahead.
All really good comments. Let me save you guys a little bit of trouble. I see that right now, I think in the original description, I said 4 outlets. You can knock it down to 2. I think that'll save you some trouble. And if you can put them on opposite sides of the table, that'll probably help in terms of utility. Does that make sense?
Yes, it does.
And I really like that you've put it into a box. I think that that's going to keep a lot of dust off of the out of anything that might be inside your box. Another thought, I like the idea of the spikes. You might consider like some kind of a flip down so that you can use the astronaut's weight to kind of, put their foot on it and push it down a little bit. That might help make it a little bit easier to level it the way they want. Does that make sense?
Yeah, it does.
I was gonna say the same thing. Additionally, here's a couple of thoughts that I've shared with some teams. If you look online at the type of extension cords that are used for a trailer or an RV that goes into a powered up campsite, you'll see that the extension cord has it's a three-pronged, cord that you normally think of that's grounded, but it also has a screw cap on it. So it's almost like when you're attaching this, it's similar to like hooking a garden hose to a water bib, right? It twists on, and that gives you a really nice secure connection, right? And that's so somebody doesn't come along and inadvertently kick this thing and disconnect it, etc. Now, NASA may come up with some modified form of that, but if you have even just an image of that to show that kind of connection, it reinforces what Florence says. You want to make sure that, because again, an astronaut walking around, there are a lot of things going on. It would be not unlikely that they might hit that cord and just pull it out of a socket, right? So that's a thought. The other thing is, keep in mind that the table itself, the tools they're going to be using, like let's say just a hand drill is a good example. Most people don't use a hand drill that actually has a cord to plug in anymore, right? If you go to a hardware store and buy a hand drill now, you rarely even see those because we've come out with all sorts of battery operated tools, right? So you might want to think of incorporating into your table, instead of just an outlet that you plug something into, a charging station. And that way they can, they'll have a variety of different tools, but you could have one universal battery that could fit into a hand drill or anything else. And that way, when they start to lose power, they've just got to take off one battery, put it into the charger, and take a fully charged one and put it back into the tool, right? And you can simulate that as well, because I'll bet, if you go home, your parents probably have either in the garage or the shop some tools, and I'll bet you $1 you've already got a battery operated system like that, right? So you could borrow that charging station to just kind of set on your prototype to simulate that whole notion, right?
Hey, tell me a little bit more about the how the cord is stored. How did you guys plan on that again?
So the cord would be either right here, or it could be on a different location. We wanted it on different sides of the drawer. So it basically look like a hole in the middle. So it'll be around a, what's it called? A rotating like axis that you can pull it in. And then when you let go of it, it goes right back. Kind of like when you use a vacuum and you take the cord out and then it retreats back. So we were thinking that would be the easiest way for them to for the cord to be stored and to be used.
I think that's a good idea. Just because of dust, you might want to also consider having like some brushes on there or something, so that as the cord comes back in, it kind of knocks off some of the dust. Does that make sense?
Yeah.
Okay, good job. Now, also tell me about the, right now you've got like a green plexiglass for the box. What kind of ideas did you think about the material for the top surface? Did you want it to be transparent? Or did you want it to be more rigid? What do you guys thinking?
I wouldn't think of transparent, even though it would be a good idea to see the drawer and like give the other tables. I would just leave it as like a non-transparent, transparent material just in case. But I do like the idea of the transparent. I would have to do more research on that and see what the outcomes would be for that.
Well, and part of what I'm thinking about is that if you've got your light set up so that it's inside of a transparent material, it can also work as dispersing some of that light. And so it would even out some of those shadows without light shining directly up into the astronauts' faces. And so I don't know if polycarbonate is going to be strong enough for that kind of thing, if it's just going to get overly scratched up or something. But even if the surfaces get scratched, it's still dispersing the light more evenly. And so it's something to consider. If you think that it's more important that it's made out of aluminum or something like that, so that it's a more rigid surface, I'm okay with that as well. It's just something for you guys to consider. I think that I really like the box design, that everything kind of folds up in it, just because it makes me feel like when you're bouncing down the road trying to get to and from your work site, you're not going to be losing parts. I think you've got some great ideas here. Excellent job, team. I think that you've really incorporated and demonstrated how some of these things would fit together. Even though this is a very simple kind of prototype, it really gives us a good visual idea of what you're thinking about. And I think that that's most important for you as you move forward. Excellent job, team. Thank you so much.
Can I just say one thing? So
Yeah.
the lamp itself, since this is the cover, it would be on a gooseneck, so it's high up so that they can see
Yeah.
over the entire table. So I feel like unless the lamp then is like flipped over in a certain way to illuminate the table, I'm just not sure how that would work.
No, I think you're right. You've got some good ideas. Having a gooseneck available that could kind of flip out and look down, I think is a terrific idea. And that's one of these difficulties. There are 100 different ways to be able to set up these lights, and until we start using one, we may not even understand exactly what we want this lamp to do. So it might change out even as we develop. So keep that idea and then also consider others. But I think that you guys have an excellent design here. Keep going with this.
Thank you. Really
Yeah,
appreciate that.
and I do want to recognize the other members of the class.
Yeah. Where's the rest of the class? I see one or two behind you.
Tell us, just tell us what part of this project you are working on. Like,
I see that you guys develop it throughout the whole class, and that means everybody's ideas have a lot of value.
Yeah, so basically what we did was we split it up into different groups and teams, and we had like a research team, so people research materials for the like different, like the top part. A group researched that, some research for the legs. We had a CAD team, a design team for the brochure, the PowerPoint,
The 3D model.
the 3D model. Those are pretty much
The
so.
build
Yeah,
team.
the build team. So we had the different
Very
ones
smart.
and came together. Yeah.
And just so you realize, that's very similar to how we would be doing it here at NASA or in any of these other companies that work with NASA. I think that you guys are getting a good experience where you're spreading out the ideas and the capabilities throughout several people. I mean, when we're developing stuff for HUNCH, it's we've got 20 people that are all involved in one particular project. And so I think you guys are doing a terrific job.
yeah,
Thank you.
yep. I really like that you have those different teams all working together. That's an important lesson, how to be a team player. So great job. I really appreciate all your work on this. Do you have any questions for us?
So a couple questions were answered like from the group before, so we got those, and the only one is for the LED, for the light, should we use solar LED lights, or is there like a different type of light we should use?
I'd say research it. You guys come up with what recommendations you think are best, right? That's what we're looking for, is your innovation and your ideas.
Okay.
Right. We have never built a work table for the moon yet. You're the first. So whatever you find, and you have a research team, find the best. That's That's what we want you, and I think the gooseneck lamp is a really good idea. Because you can move it around, you can bend it, you know. It's really cool.
You know, one other thought, with the lights, every time I pull out the work table, I may not need to plug in. Maybe I'm just pulling it out for a few minutes. So it might be valuable if that work table light was battery powered. And it might be like Dave was saying with, you know, one of the standard battery, one of the standard batteries, so that they're all using the same thing. But I don't think that we should have to plug it in every time that we want light. Does that make sense?
Mhm.
Yeah, that makes sense.
And it reminds me of a light that I use every day on my desk that doesn't have a switch. You just run your hand over the part that turns it on and off. That would be really better for an astronaut than in a big glove, you know, turning a tiny switch. This, you just, it's by my bed. And I don't have to look at it. I just run my hand over it. It turns it on or off. It's crazy, but that's pretty cool. That was from Costco, actually.
Good thought.
So
Right.
to add on to your question, would it be better to have more than one? So we'll have like the battery powered for like long time that you're gonna be using it, and solar, so that when it's only gonna be for like a couple of minutes, it'll just turn off right then. Would that work?
I think that that's a decent idea.
Uh-huh.
Yeah, play around with some of these ideas. Don't pretend like I've got all the answers. That's for sure. Another thought, I would bet that, does anybody have like a portable work table at their house that they use, or that their mom or dad uses on occasion? I happen to have one, and there are things that I like and dislike about it. And you might go to that if you've got somebody down the street or somebody in the class who's got one. Find out what they like and dislike about it. And that might help you out also.
So should we also have like maybe a light underneath the table? So if things fall, because I don't know if it's dark up there. So if they fall, okay.
I think that'd be valuable. Sure.
Okay.
Your gooseneck could possibly do that too.
Yeah, your goose, that's an advantage of the gooseneck. Just bend it down.
That's right.
Oh,
Yeah, I don't know about you guys, but it's when I'm on a project and I'm trying to get done before it gets too dark, the tools and the screws always drop in the darkest place I can find underneath my workbench. So
But I also like your draw. That's very clever too. Use up all the space in your suitcase, you know.
Absolutely.
I think so. Okay.
Okay, well, thank you all so much.
Excellent job.
We really like your work so far.
thank you.
Thank you.
Yep. And you can always ask me questions, just email me.
Well, just real quick, are
Sure.
there any other lunar work tables today, this morning? No, right?
Well, let
I saw-
me check my schedule. There is one at 1:45 your time.
Right, which is a different class. Okay, but
Yeah.
you'll send me the videos anyway, right?
Yeah, I'll send you the links to the videos. I've been getting them out real quickly.
Yeah.
I'm really good with YouTube now.
Okay, Flo, thank you very much. Thanks, Glenn, and everybody else. I appreciate your help.
Thank you for
Thank
having
you.
the kids
Excellent
work
job
on
with the
it.
team.
Have a good day.
Have a good one.
Thank you. Okay, so now we're going to move on to Mr. Bauer's class again. I believe he has a dice team that's, if they're ready to present.
Can you guys hear us?
Yep.
Okay, we just need like another few more minutes to get ready and we'll be ready.
You bet. So do you have the M up? Because I see an M for some reason.
No,
that's not-
that's not one of us, I don't think.
Oh, that's Mary Ann. That's why the M. And then Billings has a dice team that's going to present after them. And I see them on. Good morning, Billings. Oh, we have a lot of Montana teams presenting this morning. And then we're back to New Jersey. Yes,
guys
we
seeing
see it. Yes, we are. Thank you.
Um, so I'm Ben Hogan, the team lead,
I'm Michael Forward.
I'm Troy Duffy.
I'm Ahmad Faridi.
and this is Council Rock South's Micro G Dice team. So some of the problems and requirements for this project include creating a method to roll dice in space to help promote better mental health. We want to keep the randomness of the dice in place, work with any kind of die between a D4 and a D20. Keep the feeling of the rolling dice alive with it. Be able to hold at least 6 different kinds of die. Not leave any residue, whether that be chemical, magnetic, or electrical on the die, and be simple and easy to use.
Okay, so like in our process of designing our prototype, we initially looked into magnets to magnetically draw the dice back down to the cup to be able to read them. But we ran into problems in making that random, which we're going to address on the next slide. And then our other thought was to use some sort of sticky substance to adhere the dice to a container in some way. So you could have one side facing up and you could read it that way. But that had problems with this goo rubbing off, needing to be reapplied, or just messing with randomness as it built up on the die. So what we ended up going with was a container where we decrease the volume with a plunger of sorts, so you can press against a clear screen to read the die. And so this is kind of, magnets was one of the methods of rolling these die that we really felt was promising at the beginning. And then we looked into it, we realized that if we put a magnet in the base of a cup, and then we put a magnet inside the die, especially if these are permanent magnets, then they will always land north facing south or south facing north. So it truly won't be random. And then we also thought about using a ferromagnetic material instead of a permanent magnet inside the die. So that way you could get a temporary magnetic field. But the electron alignment from a previous roll could affect the randomness of the next roll because it's already got an induced magnetic field that might not have fully vanished between rolls. So we felt this wouldn't maintain the randomness of die.
So our prototype has 3 main parts. There is the plunger, the cup bottom. Yeah, a little bit. Let me see if I can actually fix that. Sorry, our camera's a bit off, but we're realizing.
Show them to us after your
Yeah.
PowerPoint so that your
Okay.
screen is bigger.
And the cup. So the cup acts as like a secure area for the dice to be contained. The plunger will propel the dice up to the cup bottom, and the cup bottom will allow for the reading of the dice. And will allow for easy access of the dice so more dice can be added or removed. And these are the parts of the prototype. This is the cup on the left, the plunger shaft and top, and the cup bottom. And some of the inspirations for this prototype included the Yahtzee cup with how it held dice. We felt that could be applied well into this project, as well as the syringe with how it kind of decreased the volume of the liquid in a syringe. We felt that would also fit well with what we were thinking of doing. And here's a few videos of our prototype. The first one is an assembly video. You put the plunger shaft through the top hole, and then you put on the plunger top, and then you can screw the bottom on to the bottom part of the cup. And then And then here is a video demonstration of it in action. So this is Council Rock South's micro D dice prototype. How it basically works is you put however many dice you want in there. For example, we have one of each kind of die, a D4, a D6, a D8, 10, 12, and 20 in there, just so we can show that it works with every kind of die. And then you seal the lid, and then you shape the container, and then you push up on this plunger here to propel the dice to go towards this clear acrylic top, and you can read your scores.
The pros and cons of our device is that there isn't any residue from a sticky substance or magnets, as explained before, that would cause issues. It's small and pretty simple. It can hold up to 6 dice of any kind. It keeps the feeling of rolling dice, and it's fun to use. The only issues is that it can be hard to hold if you have small hands, and as the picture shows, the dice can sometimes stack on top of each other when you try to push the plunger. For our prototype, we're currently using a Tallman T-Glaze 3mm filament. Possible materials for the cup or cup bottom can be acrylic, which is clear and durable, and it's fairly cheap, or polycarbonate, which is also clear and durable, but can cost a bit more depending on the quality.
So over the past few months, we've had some evolutions in our prototype. For starters, with the cup, we realized it was difficult to fit all 6 dice in our original size. So we decided to increase the size of the cup. Alongside that, we increased the size of the cup bottom and created a setup so it can be screwed in, as well as adding a acrylic lens so that you can actually see the results on through the bottom of the cup. And for the plunger, with the changes to the size of the cup, we decided to make it the length of the shaft a bit smaller, as well as increasing the disc on the bottom to be a bit bigger, so that no dice would get stuck in the with the plunger going down. And this is a before and after picture. The picture on the left is our original prototype, and the picture on the right is our current prototype. And then over here, there is a unassembled version of our first prototype, as well as a unassembled version of our current prototype.
So for this project, we obviously, because this is going to be in microgravity, we researched methods of simulating microgravity here on Earth. So the most effective method that we found was the plane that goes on an elliptical flight path that simulates basically weightlessness through the way it flies. But obviously, for our means, it's very expensive and unobtainable. So the next thing we looked at was something called diamagnetic levitation, which uses magnets to basically put something ferrous in a state of equilibrium. But as we stated earlier, for our prototype it wouldn't really work with magnets in the sense that the dice, it wouldn't guarantee it to be random. So that wasn't also going to work. But then we found that astronauts on Earth use pools of water sometimes to simulate the environment of microgravity. So for our project, we decided that that would be the most effective use. So to test the randomness of our prototype, we began to develop a way to get one. So we filled a large bin with tap water, as seen on the screen here, and we placed one 6-sided die into the prototype, and we rolled the die in the prototype 15 times between 4 different people, 50 times for 4 different people. And after rolling, we averaged out the dice rolls and made a histogram. The average roll between 50 rolls was 3.7, which was 5.71% higher than the actual average roll of a single-sided die being 3.5. The experiment was also done with 2 6-sided dice, and it resulted with an average dice roll of 7 between the 2 dice. And this was exactly the same as the expected average.
And here is a video of us of how we demonstrated our prototype.
I screw on the lid. For our testing purposes, we are using water, top of it, simulate low gravity.
Down a little bit more.
That would be a 6. Then we repeat this several times, all the data into our graphs. All the data here is in the graphs on the right. Okay, so here are the actual graphs. So the one on the left is just a single die rolled in our prototype. And you can see it's a fairly uniform distribution of the dice rolls between 1 and 6. And the variation we get here, we expect that's due to our limited sample size. We only did a total of 50 rolls. But if we were to go to larger values like 100 or 500 or even 1,000, we'd expect a much more even distribution. And then on the right, these are the results with 2 dice in the container to try and test the randomness with 2. And so the expected average roll for that is 7, which we got. It does not quite look like a normal like you would expect. But again, I think that's due to our limited testing with just 50 rolls instead of a larger number with like 500 or so.
So moving forward, we have a few future plans. For starters, we want to make the design a bit more smaller and compact for better storage and for stuff of that sort. We'll look into making the entire cup transparent so the dice can be seen for more than just the cup bottom. We want to look into ways of better testing in a micro-G environment, as well as testing further in a micro-G environment. Make the design easier to hold. Look into like alternative methods. So potentially looking back and seeing maybe if we could actually use magnets or use a sticky substance. Potentially look into digital dice and see if that would be a possible use in this project and make it look a little more aesthetically pleasing and a bit less boring. And that's our presentation. Thank you for listening. And do you have any questions?
Wow.
Nice.
This is the most thorough presentation I've seen.
Thank you.
You guys have done an outstanding job.
I love that you've gotten to testing already. I think that's
Absolutely.
terrific.
There it is. That's a little more focused.
Yeah, and especially the water testing was nice.
Yeah, we definitely wanted to really try to get testing as fast as possible because we wanted to make sure we didn't want to like invest a lot of time into a prototype and then not test it. And then when we eventually get to testing, we find out, oh, it's not working. So we wanted to really try to get on that as fast as possible.
Very good.
Guys, can I ask a question? Because I've seen this come up before. I'm not really a gamer and I'm not familiar with a lot of these different sided dice. One question that I have is with this plunger and you've closed it down and you now have all of your die trapped. If you've got something like a pyramidal shaped dice, right? Yeah. Are you able to get it so that you have one side facing the acrylic so you clearly know which value you're supposed to be measuring? Because it seems as though in many cases you're going to have, the plunger is going to have a flat portion and then you're going to have a point at the top, yeah, which then creates the issue of, okay, which side am I actually going to measure? How do you deal with that?
So this was a concern I had before I started, even because I also really didn't know even how to read a 4-sided die, which is a D4, which I'm showing here.
Yeah,
which is what you're talking about. How you read it, I looked into. You actually read it from the top point. So for example, I'm going to see if I can get into focus. This point right here you'd read, which is a 1. So when it's propelled up, you can, in theory, let me just see if I can show it as an example real fast. You are able to see the
hey, could you stop sharing a little bit so that we can see this on the bigger screen?
Oh, yeah.
Yeah, so that when you're demonstrating, it'll be a little easier to follow. Great, thank you.
No problem. So I just put a D4 in here, and then if I shake out the container and then propel it upwards, let me see. You can kind of, it's a bit hard to see with the camera quality, but like you can see the point pushing up, and you can see it's hard to see the number from using the camera, but there is a 3, and that's how you would record that.
Okay.
Number.
All right. Thank you.
No problem.
I am a gamer, and I'm impressed with what you got, what you've done there.
Thank you.
I have my own. I'm very curious. I like the plunger idea. I like the fact that when you push it down, you can set it like push it against the table, it all pops up. Taking that a step further, could you roll the dice in there, set it in the plunger, and have it like have something that it goes into that holds the dice where they are, so that you could add the dice together if you have a bunch of them, or see the dice, kind of like a resting spot that you could do that. Is that something you considered at all, or no?
We did kind of consider that. We were thinking of methods of making it so potentially like once you let's say once you push it up, once you push the plunger up, you'd be able to like essentially detach the bottom, and then you could actually like look at the bottom here and like see what your results are. That's something we considered. We haven't looked into it a lot as of recent, but it is something we have briefly looked into.
Okay, I'm really impressed by the amount of work you guys put into this. I like it. I like the fact you can hold it in your hand. The fact that you've already identified, well, some hands are smaller. The last thing I wanted to suggest there is kind of looking at how much time does it take. For example, if you're playing a role-playing game and somebody says you got to roll 66, okay, how much time does it take to load, shake, and roll for yourself there? Because if it takes several minutes, then you've kind of taken away the fun of the game.
Yeah.
But if you can do it quickly, that adds to it. So have you thought about that or done anything with that?
So we haven't timed it per se, but we do feel like if I grab out right here, I have six-sided die actually. Now, obviously, this isn't in a microgravity environment,
right?
But I would assume it's at least not impossible to quickly just put your dice in there in the cup and then seal it. And if you want to like change the amount of die, you could then open this back up, quickly put your die in, and then reseal it.
Okay.
Use the lid with the screw design, so it could be opened and closed fairly easily.
Very cool. I really am impressed. It's got me thinking about other things, like ways to store your dice when you're not rolling them and things like that. How to easily dispense them, like maybe a chip counter type thing, that you can slide the dice out of to put them in here when you're counting out 66. Because in space, it's not going to be easy. You can't just leave them in your in a box or something, or a bag easily. So nicely done. Very nice job. I'm sorry, Glenn, for taking up too much time here.
No. All of these are great comments. I really like what everybody said. I like that you're wanting to have it transparent the whole all the way around. I think that really adds to the confirming that it's a randomizer, right?
Yeah.
And I think that so our number one thing is randomization, and you guys are way onto that. The second part is fun, and I think that you guys are working on that. It's hard to engineer fun. And then you're also thinking about style already. And, that's another part of that fun. And it's, so my thoughts on, do you have some ideas of how you want to stylize it to keep that fun involved in the product?
We haven't looked into it a lot in particular. Our first priority with this project was to really get down the concept of like how this would work, and really look into that. Pretty much our next step, now that we've confirmed this, is to both test it even further to further confirm that it is truly random, and alongside that, look into making it more aesthetically pleasing. But we haven't looked into it a lot yet, no.
That's just fine. So just some thoughts for you. Is there 4 people in the team? Is that correct?
Mhm.
Okay, so all 4 people. So you guys can all think on this. One way that you get a dice tower is it might look like a castle, or it might look like a dragon, or maybe a gauntlet or something like that. But of course, you guys are the first ones going to Mars, right? And so what does your dice tower, what does your dice thing, what do you want it to look like? Think of yourself as the astronaut, and that you are, what do you want your dice machine to look like, so that everybody else wants to use yours, as opposed to, or, you know, and the potential is that if you've got 6 people going to Mars, each one of them has their own dice holder, right? And so think about what kind of dice holder you think is going to make it feel like this is the coolest dice thing ever, and it's going to help us have a good time as we're traveling. Does that make sense?
Yeah, I gotcha. Thank you.
For some people, it might be make it look like 1920s Flash Gordon kind of thing, right? Somebody else might make it look like Star Trek, and you know, I'm okay with whatever it is, right? I talked to one guy, and he was thinking, you know, this rapper has this really cool style that he has. Can we have, you know? And so he's thinking of like gold and diamonds and all kinds of stuff, and I'm going, hey, I'm okay with that, right? So whatever makes it feel like the fun is coming with you is what I think you're looking for. All right.
Alien xenomorph.
Yeah, so that reminds me of years ago, maybe 10 years ago now, one of the students at Council Rock was a big Doctor Who fan, and she made a Doctor Who phone booth. So that's the type of thing we're looking at here. I don't know what you're fans of, but something, you know, like you're a fan of, and use it.
Yeah.
You know, it's funny you say that. I know at least one of our astronauts is a big Doctor Who fan, and we had talked about making, you know, how can we make one of her rooms in her house so that you enter it through the booth and then it just looks, you know, much bigger kind of thing. Anyways. Okay.
Thank you. Very nice.
I like what you're doing. Keep
Yeah, and I was impressed with your PowerPoint, and the videos work beautifully. You've done a lot of work. We really appreciate it. Thank you, team. Okay. We will move on if you're.
Nicely done.
Yeah. Thank you so much. 2 thumbs up. And we're going to move on now to Billings, Montana, and they have a dice team.
Okay.
They actually have two dice teams, but oh no, just one.
Team.
Yeah.
I'm Nolan. I'm part of the dice group for Billings Career Center.
And I'm Tyler.
My name is Daniel. Yep. All right. So this is our defining the problem and some early ideas. We already know that you guys know a good chunk of the problem. We have to make it randomized, and there cannot be any residue like magnetics left over. There can't be anything sticky. And we really stuck to the idea of make it fun, simple, and extra uses for more games. So through that extra uses for more games, we defined our idea as how much fun could you cram into a box. And so this is some of our early ideas on the right. We have a dice bat, handheld wind tunnel, squeeze the ball and it glows, blender for testing, and some of these ideas, not all of them naturally, made it into our first prototype.
This like plastic thing that goes into the light. He's obviously not using this light. Oh, we could use it to disperse it.
Times in our color-coded list on the previous slide, we created a decision matrix where we kind of talked through the different aspects to a prototype, and we decided that our best option was a modified billiards table. On the left in these green and pink images, you can see kind of our rough designs of what we were going to do. Our first concept for the billiard table was kind of like a smaller version of your typical one with the pockets. But we thought in a micro G environment, trying to get these dice into small pockets would be hard. So we decided to do more of like a trench approach, which you can see the shelled out bit of the trench in the green image. But again, we were trying to have a hard time figuring out with these dice floating in micro G, how would we get it into our prototype? So we decided to do a redesign. And we talked about different ways we would get it to move and decided that using suction and just general air power with a fan would work. And so next problem.
So this is our redesign. And the whole idea of it is that we'll have like a meshy fabric over and then a fan below that sucks. And then you can roll the dice in there and eventually it will slow down to a stop. And the first part is the wall, and we're using a peg and hole system to hold all these pieces together. So you can connect all the walls together and then put it on the second piece, which is the base plate. And then the third picture is just the whole thing built together. And then the fourth picture is the top, but we did eventually redesign the top because that was a little too hard to make. And since we redesigned the top, we decided to use plexiglass. And that last piece is what would hold the plexiglass in for the top.
All right, so with our fan mechanism, Nolan, who was just speaking before me, had suggested we use a nocturnal fan. Just basically a small, easily electronically powered fan, kind of used for like PCs and such. And we decided that we wanted to try to reverse the polarity of the fan blades, so that we could have, to randomize the dice, we would have it blow within the cap portion. And then when we're ready to read the dice, we would reverse the polarity, which would cause a sucking force, which would draw the dice down to our mesh netting. To keep the, we had the netting to keep the dice out of the fan blades, obviously, because that would cause a lot of damage. So we would have that blow to randomize the dice, and then we would flip it to suck, so it would pin them down to the mesh so we could read it.
So obviously, if we're gonna have a fan blowing air out of the bottom, we need some way to secure it. So we're gonna connect this first image, which is a screw, to probably the side of the of our project, and that screw goes into the connector for the rail system on the space station. And yeah.
This is an expanded view of our prototype.
Yeah, this is
yeah. So that that kind of pyramid area where the things connect, that is where the mesh is going to be, and that is where the die will be able to run. So once they start sucking down, they will go into that mesh, and then they will be able to be read. Just play button.
Yeah, try to play the expanded view.
In the bottom. Yep, that part that's moving up.
Yes, so we have the netting nestled between the main box and the pyramid structure.
It's really slow. I'm sorry.
Yeah, that's just kind of seeing each individual piece. As you can see, we kind of stuck to that peg and hole system for assembly, just to keep it simple. That way you don't have to have any screws or special parts to assemble it.
You guys want to show the prototype?
Yeah, we can. All right, and then this is what we have.
3D printed so far.
Yeah.
All right, so first things first, this is our base plate. The fan will go right up here, and these two pegs on each of the corners are what the walls will go on. This is our current fan. So this will be spinning either counterclockwise or clockwise, suctioning or blowing. And we had to create this right here so that it would actually have the air system. I'm gonna move this out of the way temporarily so I can have the walls. These are the walls. The pegs go here, and the other walls connect with the pegs, which will look something like this. One peg is connected. All right, there you go. So this is our current box. This is it on the side. And if you are worried about the box coming apart through the pegs because they are not tight enough, that is not a worry. They are plenty tight. I know this. I'm the only person on my team to actually be able to assemble this box. And so the fan would snuggle right in here. We still have to make the area where the fan would actually connect to the inside of the box. That connector piece that we were talking about that allows us to put it, yeah. Attach the plexi would go right on here. That skeleton or that plexiglass would kind of like pyramid up. Yep. So the fan would cover this entire area. And for other uses of like games and whatnot, I was thinking that we could just have it on like the side and we could just flip it upwards using a joint. And we have yet to print the joint, but as an example, I have this, which is definitely not a toy of any kind. It is a that once
I have one of those, I think.
it is 2015.
Yeah.
This joint allows for easy posability of just one plane up and down, but it will not just randomly go fly off and be very, very loose. It will stay in the position that you want it.
Okay, so let me ask a little bit. So when you put the dice in, you're wanting the dice are going to get sucked down to the bottom where the fan is. Is that right?
No.
So.
Or are they going to get blown up to the top?
Yeah.
So with the prototype we have now, we have our box, and then we put a mesh netting to separate the dome from the fan, and then we'd attach the plexiglass cap so that the dice would only stay between the mesh netting and the cap.
We still have to get that mesh netting.
Yeah.
That's the
We still mesh netting and construct our cap. But
Okay, and whether you do a mesh netting or you put another grill on top, I think that that's a great idea. See, you might be able to cut down on some of your grill so that you get more airflow so you get good. Well, so first of all, your grill is keeping people's fingers from getting, rubbed by your fan, which I think is great. And then the mesh netting on top, I think would be adequate for your dice. I think that all sounds good. I like your box idea. And so then the transparent, you've got 4 transparent pieces on top, correct? So that you can see into it. Okay. And then what goes in the center? I didn't quite understand that. So at the very top, there is an opening.
yes, you could drop the dice in that hole to get the dice in the thing in our prototype. And in order to use the dice again, you could either remove the cap and grab the dice out and re-put them in the hole, or you could just restart the fan again and randomize.
And that sounds good. Now, what type, do you need 2 batteries, or what kind of batteries do you need to operate your fan?
So right now we're using a power system to power it, but eventually we would like to get to something that uses batteries.
Okay.
Yeah, our teacher just stepped out to grab our power supply, but that's what we've been using thus far.
Maybe it's not.
Which
And
is
that's
a-
fine.
It's
And
not-
so just make sure that you have a plan for how you want to place the batteries so that they're one, kind of out of the way, but also so that they are easy to access so that you can change the batteries as you need. Make sense?
We could probably either have them like on the sides here, or maybe on like sides here. Maybe even like have like a cap so that they go here, but we just have a cap that goes on top of them, so that you
Sure.
can just you need if need be. Kind of like a remote.
I like all of those ideas. I think that those are all very easy. And then also plan out, where do you want that switch so that it's easy to handle and it doesn't get bumped accidentally or something like that.
Well, our current fan actually does have a little button to control the flow of power.
So you've just been like redirecting that here.
I think that's a great idea. The fact that you've already got a switch on it makes it easier. And then just place it so that it's an easy place to reach. I think this is looking really good, team. The fact that you've got some things built and you've got a way to be able to visualize and handle it all looks really good to me. Excellent job, team.
I have a question. I'm sorry, go ahead.
Oh, I was going to ask, is there any specific types of games that you would like to play in space?
Yes.
What would they be?
The fun ones.
I love it.
Basically plan for a whole variety of different types of games and different types of dice for this. This is kind of like this. Think of the dice are the essential part of a major collection of different games, and so that's one of the reasons we had this. Is if you're going to have games in space, let's start with the dice for fixing potential problems, and that's where we're at with this.
And we do have all of the types of die, all 6 of them. There's 6.
Yeah, there's 6.
You just got them. Right. Got them right here that we've been using as kind of like reference points to how big we should size it and whatnot, so that they're not, so the box is not too big or too small.
Right.
And also, types of games, we've definitely been considering card games. But with Daniel's fold out sides we've been discussing, you could also do like chess or checkers. And more like tabletop based games like that.
Or we could have it as like a blank slate, so that some of the astronauts can like draw their own template on and start playing what they like and start making their own games if need be.
My question for you in this is when you're swapping out dice, for example, let's say one night I want to play Yahtzee and I have 5 dice, 5d6, but the next night I want to play Dungeons and Dragons. And so that game has the whole collection of dice, which changes every few minutes. Swapping out the dice, have you timed that kind of like how much time would it take to open it up, put dice in, put down? Because that changes throughout the game.
Yeah, so we haven't built our clear cap yet, but that will definitely be something we time when we do get it constructed.
Okay.
It's the thing that's going to take the longest amount of time is getting that cap off, because since it's 0 gravity, these dice won't like go down, they won't like move everywhere. You'll probably just be able to grab them, place the die in, and then close it back up again. So at most, if you're having a hard time getting all that, it's probably going to take 30 seconds. If you have like standard time, I'm guesstimating basically like probably 10.
Okay, that's something you definitely want to test when you're going through it. And my last question is, how are you, if you have a bunch of dice you toss in there, how are they being held still to be able to be read at the end? I didn't quite get that.
The suction power, the fan would suck them against the netting.
Okay, so that's going to be, you're talking about with regular dice, that would be a pretty strong fan. Are we
We're-
talking-
We're trying to get a pretty stronger fan because this isn't as strong as we would like it currently.
Yeah. And the reason I'm bringing that up is plan and definitely test with this, like throwing the dice sideways. In gravity, it will pull them down, but you do not have to be, you're not restricted to over the counter type dice. So you can actually play with the dice material and things like that might help with holding them, making them lighter or something along those lines. So that's it for me. Good job. I love the fact that you've got a built prototype here.
Thank you.
So my suggestion is, first of all, this is the first one of these systems that is kind of using a mechanical method of, moving the dice with the fan. And I'm actually very intrigued by that, right? There's a notion that, one of the things we want with this is to simulate the idea of somebody rolling dice and throwing it with their hands. But, there are a lot of games that use some kind of a mechanical system that people really seem to enjoy, right? So my suggestion is, once you get this thing fully operational, do some subjective testing, right? Get as many different people, pardon me, using this thing and have them rate this, right? Because ultimately it comes down to anything else. Whenever something new is developed, it's a matter of, what's the interest level? And I can see this as being a potentially, engaging type of gaming system. So, but I really think you guys are onto something there. And, because of the fact that we're talking about, human preferences, what's the excitement level, the engagement level, make sure that you incorporate that into your testing phase, because that's going to be an important part of it. It shouldn't come down to whether one of us finds it engaging or not. That's an N of one, right? That's not very comprehensive.
Yeah.
And if I might interject right now, with the noise the fan will be making, and with that fan blowing, the dice will inevitably hit the sides of the plexiglass and probably make some sound. So we're guessing that would be pretty.
Yeah, well, again, I think some people are going to be very, some people will like that, others won't. But, I think that subjective data is going to be helpful, right?
Yep.
Yeah, especially since the project is meant to boost astronaut mental health, we'll definitely want to see what people's emotions behind it are.
See, and I think if it were silent, they would not like it.
Yeah, I agree.
I think that the rattling is actually an important component. The question is how loud, right? Some dice cups are kind of padded a little bit, but you can still hear them well. So it's going to be something for you guys to consider.
Thank you. Thank you. All right.
Okay, thank you so much. That was a really good demonstration too. And an
Excellent
explanation. Yeah, a really good job. All right, and we have another Billings team going to present right now, and that's our Auger team. Thank you, DICE team, so much. Great job. Introduce yourselves before the PowerPoint.
All right. So I'm Lake. I'm
one of the team members on the Lunar Auger project. I'm Chase. I'm JJ. And our project is the Auger. So the problem is we need to get the lunar regolith into like a brick shape, combining it with plastic and heating it to a slurry so that it can be extruded into a brick. So this is a demonstration of our pressing method. So we would be mixing it up within our auger and then pressing it into this brick mold. And press it into this brick mold. I'm just doing it with my hand right now, and it's very cold.
It's snow.
So we're pressing it down here, just compacting it into our brick shape. And then once it's all compacted down, it comes out in a nice solid brick here.
Wow. That is cool.
Very good.
And for our current problems that we have on the auger is that it's the auger that we currently have isn't actually that efficient, and the design that we have was actually very prone to clogging onto the back end of the auger, which actually caused it to jam a fair bit. But with the snow, it wasn't too much of a problem, but with the sawdust that we used, it was actually a fair bit of a problem. So we made a plan to make the auger larger, along with making the tolerance a lot smaller, since it's actually a really loose fit for our auger currently. And the press also did not have a way to slide backward. Well, actually did not have a way to stop itself from sliding backward, meaning that if a person were to, if it were to slide back beyond this point, there was actually a chance for the auger, no, not auger, the press to get stuck and maybe like twist sideways. And you can kind of see that in the snow video. I had to readjust it.
I don't think they can see what you're doing right now, JJ.
Yeah, you can. Yeah, I can't see very well.
Oh wait, I gotta stop. And then I gotta go and share.
Yeah, this is basically the auger that we currently have. The tolerance is actually 2 millimeters larger than it should be, making this thing actually wiggle a lot.
Okay.
The problem would have just been whenever this piece was actually not completely fit, it actually twisted left and right, making our press not be able to be 100% inwards. Meaning that when you actually push it forward, there was a chance for it to get stuck and jammed.
Okay.
Back to the PowerPoint.
All right, so we'll demonstrate this. So this is our simulated lunar regolith.
Okay, just my sharing screen on the video.
Yep. Okay, so this is our simulated lunar regolith. It's just a mix of sand and some sawdust here. So we'll just put some of this into our auger, and then this would be like funnel fed as well. So it would be easier if you don't have to hand feed it. And then if I just twist this knob this way, this should, in theory, just pour some out. So that would be mixing our slurry, mixing our melted plastic and our regolith into this press here, so that we could press it down into our brick.
Okay.
That's pretty much it.
Okay, now, so you've got sand and you're using the sawdust to simulate the plastic that you're going to put in there. Is that correct?
We're kind of just using it as a filler right now. So we have like a better system, and then we will melt down some actual plastic or use some like watered down clay as a more adhesive material.
Okay, just as a thought for you, if you take, so because you've got a 3D printed auger and pipe, Obviously, you can't melt down plastic with that, but you might take something like candle wax. So if you have shaved candles and drop it into there, you could heat it up to a temperature, and you could see if as you put in your candle flakes, your wax flakes, if they actually get mixed up well enough with the sand. Does that make sense?
Yeah, yep.
Okay. So then as it pushes that slurry out, how does it get into your brick mold?
So right now, our second prototype for our new redesign for this has a higher exterior wall here that this would slot into right here.
I see.
Like this, so that when it
Okay.
goes extrude, it would get pressed here. And then our newer press has a way to cut off that flow and also press down at the same time.
Okay. Well, and this is a little bit different than I was asking for. When you think of an extrusion, it's kind of like when you're doing Play-Doh and you're squeezing out a particular shape. Does that make sense?
Yeah.
Now that doesn't mean that you can't do what we're doing, because we're really trying to produce a brick, and so it makes the mechanics of how to squeeze your brick and then how to press the brick out of your mold. That's a whole different complication. So I'm okay with that if you guys can figure out how to make the brick and be able to kind of get it out of the mold and stuff like that. So I think that that's interesting, and I think that you can play with that on this project as well. Oh, and another thought: if you end up depending on the difficulties you have with using wax in there, you might also look at like instead of wax, you might try like Crisco. It would melt at almost hand temperature as opposed to heating it up with something else. But these are just some thoughts for how to do an experiment with the materials that you have at the moment. Okay. All right. Excellent that you've got that. Your auger. You may. I like your auger. I think that that's a good looking start. I'm not sure. I'll tell you, this is the one that one of the projects that I understand the least in terms of how to produce the brick itself. That extruder, the auger getting pressure out of there is actually an important component in terms of how it gets the slurry mixed together well. And so it could be that some of that process might be dumping in a certain amount of sand and plastic and going back and forth a couple of times to be able to get it to mix properly. So these are just some things to think about. Okay. Keep going, guys. Other thoughts? Gene and Dave?
I'm really impressed with what you guys have come up with so far. The material that you're 3D printing out of, have you had any issues with that stuff breaking down at all as you're turning this and mixing it with the regular, the simulant that you're using right now?
At the moment, no, not currently.
Okay. Yeah, and I think, actually, Glenn, I think that idea of shaving up candle wax, because that would allow you to heat something to a point that you're getting good plasticity out of that wax. Yeah, one of the issues that we're having with this is it takes a lot of heat to melt plastic, right? Mm-hmm. Which your printed material probably isn't going to be able to deal with that. So I was going to suggest, taking some, modeling clay or something like that and shaving that up and using that. But I think that idea of candle wax is really good. I'd recommend you do that with your testing. Right.
I was pretty impressed by the work you've done here and the testing you've done with the mixing. It's not quite what I was thinking about for this project, but you've gone in a way that is very interesting. I'm wondering how much problems did you have with that regolith trying to bring the material down the tube, I guess.
So when we were testing with like actual coarse hardened sand that Flo brought us, it had too much abrasion between the auger and the internal pipe, so it would just get caught and you couldn't turn it anymore. So by creating a larger tube and less tolerances, there'd be less room for sand to get in and be able to stop the auger, and it would also prevent clogging within like the entry point.
Okay, I would definitely continue testing that out and try different things, because I think that's going to be a big problem for this auger on the moon, because we have no clue how that regolith is really going to work. But being able to move it along is going to be a key priority for this project. So good job.
Yeah, and similarly, yeah, one of the things that you can look at as well is it's kind of a rate of how much material you're putting into that auger. That's going to be a determinant here. You know, there's been a lot of talk about whether you want to take the regolith and batch it, and then take the plastic and batch it, and then mix those two together, or have a continuous feed. But additionally, one of the issues is what's the rate that you're going to be able to put this stuff in there? Because again, it's going to be quite easy for this thing to get to bind up, right? So that's something else you want to be measuring as you're doing this. You know, how are you going to feed this stuff into the auger, and at what kind of rate is it going to be feasible for this to happen?
Yeah.
You know, because again, you know, when you stop to think about it, if this auger gets bound up, that's problematic. It's not like you've got somebody there who can just stop and open this thing up and repair it. I mean, it's designed, you know, ostensibly intended to be kind of running autonomously. So we're going to need to know some data on those types of things.
Yeah. So as you work on this, use things that bind it up and see how you can solve that issue. That's really what we're looking for. And I also do like you're making the plunger to make those bricks. That was pretty cool to see in the snow too. Thank you for that.
Testing it with snow is a smart idea. I don't know. I don't think it'll quite stick together like that, but it's definitely worth trying out. Good thinking, guys.
Awesome. Do you have any questions?
So are we supposed to find a way to heat the material, or is that going to be done by someone else?
No, the heating is being done by a different team. Now, you still need to be able to, so however you choose to heat up yours to be able to do some of your demonstrations, that's okay with me, however you want to do it. In your particular case, if you do the candle wax or something, you know, you might be able to do something like a heat blanket, like one of the electric blankets or something. That might do as much as you need to do there.
Yeah.
Put it on kind of a low setting, I think, just to be able to get it to work though.
Right.
That way it doesn't damage your plastic. Just a thought. But how you heat it or whatever is not as important as finding out how your system works with mixing the two materials together.
One other thought, and I'm sure that this has been a part of your research, but it's going to be important to take into account, you know, the materials that the actual system would be made out of. You know, keep in mind that, you know, it's going to take a significant amount of heat to melt this plastic, you know, and it's going to be heat that has to be sustained throughout the system so it doesn't start cooling inside the auger. There's, you know, lunar regolith is abrasive, you know, it's all of those factors that, you know, what materials are you going to recommend this be made out of, and what are their tolerances in both, you know, pretty hot conditions, and as well, even when this thing isn't running, it's going to be on the surface of the moon. And that means there's going to be, you know, roughly about a 14-day period of time where it's really cold, right? So the materials component of this is going to be important to research.
Hey guys, what's so right now you're dealing with 3D printed parts. What's your next step that you're thinking about for your prototype?
So we have like a metal machining area in the career center here, and we could test out different materials there. I was thinking starting with aluminum, but then there's other materials that conduct heat better, like copper and other things like that. But those are like softer materials. They do take more damage over time.
And don't be afraid to start with steel. I mean, a steel pipe is fairly cheap to get. And then even just a regular auger, go over to the hardware store and buy a small auger that might fit in there. That's also a relatively cheap material, and it has the kind of temperature range that we're looking for. Okay. Just a thought, after you've done some testing with, you know, the candle wax and the sand, make sure you run through with some sand just to knock out as much of that wax or plastic, however you work it, just so that, you know, you don't get it all bound up inside. Okay.
Okay, well, thank you
Good job,
so
team.
much. Yeah, nice presentation.
Good
Really
job.
nice. Yep. Thank you so much, team. We appreciate it.
Thank you. Thank you. Nice.
Yep. All right, so we're going to move on to another Montana team. Brand new this year, though the teacher did it 1 year before. You might recognize him, Glenn. It's another Glenn, Mr. Bradbury. Hi.
Hi, can you guys hear us okay?
Yep.
Okay, so we're starting off with augers, so I'm gonna just turn it over to the team here. Guys, when you're ready to present, just go share screen. Okay.
All right, hello. My name is Grayson Watson, and this is Cody Wilkins. This is Christian Miller, and this is Kenny Trong, and our team name is Bricked. The problem we chose was, as you know, the problem we chose was the lunar pipe auger extruder, and we're supposed to make a 2.54 by 2.54 by 12.7 centimeter brick. We're going to be mixing fly ash or lunar regolith, sorry, not fly ash, lunar regolith, plastic and other materials to make that brick. And we're going to be using a batch system, which will have a constant production of bricks. Click share screen. There you go. Sure.
Okay. There you go.
There we go. Okay.
So you can
I apologize.
Like slideshow.
Okay, slideshow. Okay, cool. Oh.
You gotta use left click.
Okay, there we go. Okay, sorry.
Hey.
All right, good.
Yeah, that's perfect.
Okay, so there's a couple of main points that we did for research. I'll talk about a couple of them. The first one is about what types of extrusion there are in like brick making. We looked at continuous and batch processes. We chose continuous, not batch. And then there's existing commercial products right now, like the pug mill found in ceramics. There's some good points in there, which is the suction auger. It's continuous and it has like a good flow rate. And our sources were mainly from NASA and other companies that are actually making like extruded plastic goods.
The brainstorming process took about 2 to 3 weeks, and we are still going to continue that process, that brainstorming process throughout the project. As brainstorming continues, it will also continue to give us ideas on how we can change our design and continue to improve it, like final adjustments. We have some ideas that we think will work best, but we need to find the best out of those. Changes are going to be made throughout the design process. Each of these changes will help create a more efficient auger and extruder. Next slide. Brainstorming ideas consisted with different types of materials, different types of ways that we can scale down our model to a level at which we can make a functional and running prototype, where we do not need to spend as much money or do things that would be extremely hard.
We had some constraints, as Grayson mentioned, the size of the brick, and we also needed to make it as lightweight as possible, so it's as cheap as possible to take it to the moon. We also had some constraints, such as like issues of buildup of regolith and plastic on the bottom of the pipe where the auger wouldn't be able to reach. So we needed to figure out the size of the auger compared to the size of the pipe so it wouldn't have that buildup. Some other constraints we had is like that we can't realistically heat up the pipe to 200 degrees Celsius without like buying a super expensive metal or material that wouldn't melt, or a material that's super hard to contain. And we needed to, and like for accessibility reasons, we wouldn't be using the ideal materials, which we found to be silicon carbide for the pipe due to its hardness on the Mohs scale being a 9, and the lunar regolith is a 7. So there's a good range where it's better, and so it wouldn't scratch or get dinged up. So we're scaling it down to like a 1:50 ratio or whatever, but not by size, but by like hardness and materials wise. So we considered using sawdust and water instead of lunar regolith and plastic, just because we don't have to heat it and it's very accessible and very easy to obtain. So it can be extruded into a brick. It may not be a sturdy one, but as long as it extrudes and works and mixes, then it's essentially the idea of what we're working for. And we could also end up using something as aluminum or stainless steel or PVC pipe to fix that.
Some good ideas that we chose and like alternate solutions are a section auger and the flat knife cutter. There's pros and cons for both. Some pros for the section augers are that it allows for plastic and regolith to thoroughly mix. And pro for the flat knife cutter is that it's easy to produce and it has easy maintenance.
Some ideas that we have are, as seen on the screen here on the left, we have auger design that we 3D designed on this online CAD called Onshape. And we have a 3D model of it here, 3D printed with resin. And the idea behind it is that this part right here is more spaced, and each round or each blade around the auger, it's called a flighting. So we wanted to make sure that the flights were spaced apart for mixing purposes. So it would have time to mix all the materials we would have to make the right batch or idea to make the brick. So it was slightly tapered, so it has more got more time to mix and move throughout the auger. And as it gets closer, it starts to compress and gets more tapered. So it starts to bind together and make that brick that we want to make in that right size. We have the idea of an extruder die, which we are currently building on our online CAD right now. And on the left, you can see the idea of our pipe we have and the little hole in the top where we put a hopper to insert the lunar regolith and plastic and other junk to be melted down to make a brick. We are currently working out dimensions for the pipe and auger so we can build it as a prototype. So that is currently a work in progress due to the idea that we need to figure out what's the words I'm looking for? The right ratio, if that makes sense, of like mix and auger and pipe, so it doesn't like overflow it or we don't have enough.
Very good. What temperature range does your plastic have that that you've got there for the auger?
Don't really know.
You don't
Probably
really
high
know.
enough for candle wax.
High enough for candle wax, as you mentioned earlier, but
okay,
probably not high enough to melt like grocery bags or something like a
Well, and that makes sense. Okay, too. Can you scale your pipe so that your auger fits in it? I don't
Yeah.
think you want it tight, but
Yeah.
and I'm thinking if you used a steel pipe, it might be easier to heat up that candle wax kind of thing.
Yeah, on shape, we didn't get a picture of it on time, unfortunately. Oops. We do have a assembly of the pipe and the auger inside of each other, so they do fit and it's a pretty tight fit, but it does work. So we do have that.
That sounds
general.
good. And it looks like your auger needs some kind of an attachment for your motor or your hand crank.
Yeah,
did you guys have a plan for that?
Yeah, we're gonna extend the axle a little bit and then like put it through here. If we go back to one of the brainstorm slides, yeah, as you can see, if you can see my mouse, I hope.
Yeah.
Okay, so there's this little part over here where it would like go through a box into a motor and it would spin, and that's the hope, I guess.
Right. And I'm expecting that it may have to go kind of slow, right?
Yeah.
To be able to get the
slow
heat
to
transfer
mix.
that you want.
It would go slow, but it would still meet the requirement of the, how many bricks per hour was it? 100 bricks. We got like 1,400
Per day
bricks
or something like that,
24
hours.
Earth days or Earth hours.
Sure, and that works just fine. So yeah, just be aware that you're probably going to have to do some gearing there to kind of get the speed that you're looking for. Okay, excellent job, guys. Keep going.
Kenny, I think this is your son. No, that's all. That's all we got.
Okay, I've already had a little bit of talk time. Would some of our other mentors like to give their comments?
Go ahead, Gabe.
Well, I'm impressed with the design that you have there. You go back and tell me again what material you're thinking about using for a regolith simulant.
Ray, you want to pick that up?
Oh yeah, we're gonna, excuse me.
I think he's asking about the sawdust and water.
Yeah.
Oh yeah, okay, yeah, we're gonna be using like sawdust and water to be used for our you know, our prototyping, really.
Yeah, we have, there's a wood shop right down the hallway from us, so we can, it's super accessible.
So you got a big supply of sawdust. to work
Oh
with?
yeah, oh yeah.
Well, that's a good thing, you know. And here's the thing: if you guys were maybe listening on the other presentation, you know, a part of this is we're thinking mechanics, right? Where it's like driving this auger, etc. But we've also got to take into account what a mixture is going to look like and the rate at which you're going to be able to put this stuff into the system and extrude something out of it, right? So it's one of those things that it's kind of like, you know, when you're cooking or baking or something, you've got to find the right recipe here. So if you're going to use something like sawdust and water, make up a lot of different mixtures and make sure that you're accurately measuring the quantities of each that you're putting into this, right? Yeah. Because again, we're starting from zero. We've got to move forward. We don't, you know, there isn't any prescribed recipe on this kind of stuff. So the other thing is, keep in mind that ultimately we're dealing with materials that are going to be heated up significantly. So you may definitely want to also incorporate something other than water as your solvent, right? Maybe think about, as Glenn suggested before, taking some candle wax or just paraffin wax, grinding this up into as much of a powder as you can, introducing it, heating it up with something. Because it's a candle, you're not going to have to apply a lot of heat to this. You could probably wrap this in, like a heating pad or some heating coil, and see what this stuff is looking like. There are a lot of things here that have to be worked out as well. Okay.
That was part
The
of
other
our
thing
prototype.
is, at some point, you're probably going to want to, get something that's commercially available that you can use as an auger. And it's not as though you need to think about going out and trying to get some really long bit, right? You're going to be limited there. As a first step, it wouldn't be unreasonable to have a system that's only a few inches long, right? And see how this thing works effectively. Can you extrude out of it? Once you've got that down, we can, kind of expand the scale of this stuff. So keep it simple as you're getting into this process. Okay.
I double down on everything Dave and Glenn just said. One of the other things I'm starting to notice, and it has nothing to do with your project. I think what you've done is a nice setup there. And I love the model you came up with, the variation and the spacing. But the more and more I'm thinking about this is the auger, whether or not, and this is more for Glenn, is I think about some augers on Earth where there's the augers when they're spinning have a natural vibration, but there's also a lot of times they put in a vibration like an up and down vibration if you're moving it sideways and something like that to knock the grains around a little bit more. Just having a secondary vibration to keep that flow moving. So that's something I'm just throwing out there as something to think about. Could you do that, or do we need something like that to stop the jamming that could occur? So, okay.
Yeah, I definitely think that that's a great idea, Gene, that you just mentioned, because I have a bread making machine and it just has something that goes around to mix it. But I always have to take the spatula and push the dough down into that part of the machine. So it kind of climbs up the sides of that bread making machine, and I'm pushing it down all the time to do it until just initially, until the dough is really soft enough and mixed enough that it doesn't. So I like your design on your auger that in the beginning you're taking into account some of that, not doing it slower, some of it not mixing right away, and then in the end you're compressing it more. So that might solve that problem. I don't know, but it's a great idea.
Nice design.
Yeah. Do you have any questions for us?
I do have one, and I was wondering if it needs to be, if the whole idea of the pipe auger and extruder needs to be accessible or attachable to a Rover, or if that's a different project entirely.
You should be thinking about how it would attach to the Rover. I don't know that that's the main interest right now. It's more about showing us how it's going to work and seeing what kind of an auger style is going to give us the best mixing and the best compression so that we get a good extrusion. Does that make sense?
Yeah.
So, I mean, if you have thoughts about how it should be attached to the Rover, I think that would certainly help us out a lot.
Okay.
Okay. And so right now you've got the auger, you've got where the stuff comes down into the auger. Have you come up with your extrusion method or the box that it's going to come out of? What were you guys thinking there?
We were planning on using just like extruder die, which is we want it to be like a 1 by 5 inch diameter, because if it's 1 by 1, then the 5 inch outward might cause it to like bend down, which we don't want. So yeah.
We also, for cutting the bricks to where we want it to be precisely cutted, we had an idea of a flywheel cutter, which is a big blade on a bearing moving at high speed. So we would cut the bricks where we want it, and it would be like on a timer system, or it would be like a sensor of the sorts.
Mhm.
So
I think that that's a good idea. The exact method of how it gets cut is not as important to me, but seeing some of these different ideas of how to do the cutting, I think is really important. So yeah, continue working on that and help us understand how you think it could be done. I've also seen some ideas where it's kind of like a cheese cutter, where it's just a wire that comes down and cuts through it, which is also a good possibility. But however you guys want to work it, I'm glad to see what you got. Let me go back a little bit. What were you guys? So you guys are looking at sawdust and water. How are you? I'm not quite sure how that equates to a lunar regolith, which is a lot more rigid than a shavings from wood.
So it's really a scaled down idea, because if it was a possibility, our best option would be to use fly ash and actually have a plastic to melt and combine it. But since both of those materials would be a lot harder to possibly get, especially the fly ash, or be able to have it to where we could melt each of those, so that's why we were able to scale it down. But fly ash we thought would be a lot better and closer, because it has a lot of similarities with the lunar regolith. So we scaled down from the fly ash, and we're able to come up with the kind of sawdust and water idea.
Okay, and I'm not opposed to it so much, but it doesn't seem like I think that the flakiness of the sawdust may not have much similarity to the regolith. It might be better if you were going with something like a fine sand. So kind of explore it a little bit. If it's possible to get fly ash, I think I'd agree with you on that. That's a pretty good simulant. So anyways, but keep going with this. I think you guys have some great ideas here. I look forward to seeing your progress.
And since we're interested in mixing, get 2 different substances of different colors, and then you could see how well it mixes.
That's actually a great idea. I like that thought, Flo.
Yeah, I like that.
I mean, so for example, if you had like a sand, and then maybe gosh, what would be?
Or you could do 2 different color sands. You could dye your sand.
or different colored candle wax to.
Yeah, or different color candle
That's what
wax.
I'm thinking is,
Yeah.
A paraffin or a candle that has color added to it already, whether it be red or blue or something.
Yeah.
Yeah, that's a great idea, Flo.
This also goes back to something I mentioned earlier. We have to think about feeding these 2 different substances into the system, right? You've got regolith coming in, and in the final version we have plastic, right? Now the plastic has to be heated to melt, but I'm envisioning something where I think it would be easier if the plastic is somehow shredded up, ground up as much as you possibly can into something like a powder that's added to the regolith, mixed together. It's kind of like, if you're baking a cake or something and you put all the dry ingredients in and you mix them up to make it as homogeneous as possible, and then you put it into the auger and start heating it up, right? I mean, the whole idea of taking plastic and raising it to to a temperature where it becomes a fluid. It's, you know, it's liquid in consistency. That's a lot of heat. And in the little testing I've seen some teams do, you know, you apply an enormous amount of heat to this plastic to melt it. And as soon as you take that heat away, bam, it just goes right back to solid again. And you end up with, you know, this knot of plastic. So again, we got to kind of step back and think about how are you preparing these mixtures, putting them together, and then heating this up to a point where you get something that can be extruded out, right?
Yeah.
And
It's not as simple as like just throw it all in and, you know, mix it. It's going to have to, there's a process that's going to have to happen here.
And that's exactly what we do in cooking with the banana bread I'm talking about making. First, we mix all the dry ingredients together before we put it into the bread making machine.
Yeah, exactly.
That's a great point. We definitely need to be aware of that for this project.
Very good.
Okay, we're running over here. I think you have another dice team, is it?
Yeah, we do.
Good.
Yeah,
Thank
we'll
you
get
guys.
swapped over here.
You did a great job. There's a lot of conversation for that.
Thanks, guys.
All right.
Can you guys hear us?
Yes.
Just to preface, my name's Carl Paschal. I'm these guys' teacher. We've got a metals class going next door. You can probably hear that like metallic grinding noise. The metals next door has an iron worker that sends a bunch of noise over. So if you can't hear something, just ask to repeat. Thank you.
Okay. Yeah. Well, Carl, you're next, right?
But he's after our next one, right?
Right. He's after.
All right. I'm gonna get the screen shared for this team.
So we're running a little late. That's why. Can you guys hang on there?
Yeah, we can.
Yeah.
Okay. Thank you.
Hi, we're doing 0G dice for our project. I'm Judah McConville.
I'm Fisher Besner. I'm Aaron Bergman. I'm Michael Crowder. I'm Samuel Johnson.
And we are the Dice Fellas.
You should be able to hit the. Oh, you have to go to. You gotta go to Google now.
Okay.
We see your project. Yep.
So our problem was we need to develop a way to roll dice in space or a micro G environment. Because without gravity, the dice kind of there's no way to hold them down, so they kind of go everywhere. And it needs to give out consistent randomized numbers, allow for as much personal contact as possible, and needs to be used for a variety of games involving dice so that it increases the mental health of the astronauts. And all the reason of this is to provide enjoyment for extended periods of time in space or on long journeys, such as one to Mars.
So we started with research. We did some research on general information on springs, how they're working. We needed that because of, we'll get into our ideas, but there's a lot of this research is based on those ideas that we had that we brainstormed originally. We looked at materials that can survive in space, information on microgravity, information on vacuums, benefits of lightweight plastics and composites and different materials we could use that are light, easy to send up. The benefits of board games and rolling dice and how that affects your mental health. We also did some work on electromagnets because we thought a magnet might be a good idea for our brainstorming, and then types of dice and their applications.
This was some of our criteria. It needs to be able to hold like 6 dice and needs to be able to do all different types of dice so that you can play games like Dungeons and Dragons. Can't leave a residue on the dice, needs to be easy to use, and it must retain randomization.
So these are some of our brainstorming ideas. One of our first brainstorming ideas was a container-like structure with a funnel that you would roll the dice into, and then a fan would suck the dice to the bottom, and it would have a clear area to see into. one of our other ideas was a can-like structure with a plate that you would pull back, shake the dice up, and then let go, and it would spring forward. We had two types of boxes, one with Velcro inside and one with magnets inside. The Velcro, the dice's numbers would be Velcro, so it would be able to stick to it. And the magnets, it would just be metal dice. Another idea was a magnetic sheet. We had an idea of a dice with pressable buttons or sensors of some sort that would light up if it hit a certain number. We had another idea of a can with a spring, and you would pull a pin or something like that to activate it, and it would push up towards the top. Another idea was a simpler version of a spring can where there would be no springs and you would just have a plunger that would push towards the top of the can. We also had some dice tower ideas. One was with a vacuum idea, and then the second one was the same general idea, but we would have Velcro dice that would stick to the bottom of it and you would pull a plate out. And then we also had the idea of a water tube, and the dice would be flowing with the water. And then there would be a little gate that you would pull in and out that would have a fan or pump that continues the flow of water. And you would just pull that out to reset the dice. But there's some issues with this because it's not that simple, and we had much better designs, we thought. And then our dice ideas had, so one of our issues with the dice is 4-sided dice are designed to have a number on each point, and the point that's the highest is your number. And as most of our ideas had to have a flat side down, that wouldn't have worked. So we have come up with two ideas for 4-sided dice. One of them is an 8-sided dice that would have only 4 numbers on it. Another one is a 4-sided dice, but it would also have numbers on each side too.
All right, so our first idea, this is our primary idea. This is the one we're like trying to put all of our resources and time into mostly. So we're basically calling this like the spring-loaded dice cup. So right here, you'll see that it's just kind of like, imagine like a push pop, you know, those ice cream things that you had as a kid. So the top right here will be some kind of cap, right? So you'll screw the cap off, and we just have some dice right here. But you'll just throw the dice in there, and you can see on there. But you'll throw the dice in there, and then you'll pull it's kind of like a plunger, if you will. You'll pull that down. So once that is down, it doesn't show on here, but we might have some kind of pin system. So it'll like keep the spring loaded. So then you can just shake up the dice whenever you want. It's going to be like a Yahtzee cup kind of. So you'll put it in there, you'll pull that back, and then the spring will be compressed, and you can shake up the dice and do whatever you want with it. And then you'll just release it. And so the dice will spring up to the top, and it will kind of compress against the lid of this. It's going to be a clear cap at the top. So once it's compressed up there, you can actually see the numbers because the dice are going to be flat. So at the top of the cup, you'll see the actual numbers of the dice. So on this next side, these are just like similar products. I already mentioned the push pop, but I have a coffee press right here, which is extremely similar. So there's just a cap right here. You can already just take that off, right? And I have some dice with me right here, and you can literally just throw them in there and kind of, you see this and you would just press it up there. But the hope is that it's actually there's going to be an actual spring in it. So it's not just going to be pushing it up to the top. You're actually going to be, I don't know, ejecting it to the top.
And the reason for the spring is just so it's more of like a snappy feedback. It's a little bit more fun. Because if you're pushing it, it's just not quite as fun. If you have that spring, it's more of like the feeling of rolling a die.
Yeah. But one
one challenge with that is I have a four-sided dice with me, and you can obviously tell it's a triangle sort of shape, pyramid shape, yeah. And so there's points on it. So one challenge is definitely going to be trying to, I don't know, read the face of the dice, because if you're compressing it up to the top, it might be a little difficult. So like we mentioned earlier in our brainstorming ideas, we do have different types of four-sided dice that we're looking into, because that's probably going to be we're definitely going to probably have to change the four-sided dice if we're truly going to go into this wholeheartedly.
Got a second idea here. This was our basically second best idea, which is it's just got a vacuum and fan at the bottom of a little dice tower where you throw the dice into the funnel, and then it should be the whole box should be see-through, so you can kind of see the dice bouncing around. That'll be the fun part of it. And once it's at the bottom, you can pull a little drawer out and it'll keep it stuck to the bottom of the drawer, so you can read the tops of the die. Similar to products to this are just a normal dice tower. It's going to be pretty similar to that clear one, so you can just see the dice bouncing around in there. And then also this Yahtzee dice cup is pretty similar to this one and the previous one, where you just shake them around.
Finally, we have the CAD drawings, which are two different drawings for the dice cup. One is just a simple circular plunger, and the other one is more of a plus shape, which would be more durable, but it would be a little bit more annoying to use. And on the right side, we have our lid design, which is a locking mechanism that when you twist, it locks.
And that's it. Any questions?
Well, I would say that it looks like you've got a couple ideas. Have you actually built any of these at this point, or no?
Not yet. We are gonna hopefully start designing. We've got some acrylic on the way for so that we can start designing it, but we don't have a physical product yet.
Because I've seen variations on both these themes and different projects. The big thing is going to be, how is yours different from the rest? So the only way you're going to get there is by building quickly and testing and seeing the problems and the pluses that come along for both. Biggest thing is the fun factor. Remember, when you're doing this, you want to keep that fun factor going. And then I think, again, with the idea that there are several teams doing both of these these type of ideas, that what's your style? Does your style happen to lean toward a way that more people would like? So those are my only suggestions right now. Get to building and testing.
Thank you.
Dave, do you have a comment there?
Gene pretty much encapsulated it there. He's much more knowledgeable on this gaming stuff than I am.
Yeah.
I will say though that I'm interested in this idea of, some kind of mechanical system to get the dice moving, as opposed to just, physically, shaking it with your hands or something of that nature. There's something about that is intriguing to me. So I'm hoping that you can flesh that out and make it work the way you thought of it and written it out on paper. It's very interesting.
And again, I think that comes down to testing. They got to see how much vacuum do they really need to move the stuff and things like that. How much noise does it produce? And weigh the pros and cons. So.
Mm-hmm. And I personally, I see if this is correct, I wouldn't worry so much about that four-sided dice. Is that a big worry, Gene? Or?
I don't think it's a big problem. Other teams have found that they've been able to solve it pretty easily. And again, if you can come up with a four-sided die that's different for these, you don't have to go with the traditional shapes. That's one of the pages I think that Glenn put into the PowerPoint, was that, there are variations on all of these dice. My wife has a Christmas tree die that has all the dice just by spinning. So there's all kinds of different things.
Mm-hmm. Did you have any questions for us?
No, I don't think so.
Yeah, all right. Good. Well,
I
Just
would
a-
throw, guys, I would throw one caution out. Keep in mind, even if you were to create an absolute vacuum, you're not getting rid of gravity, right? So, yeah, I mean, think about it. If you go down to your chemistry department or your physics department right now, and they've got a bell jar that they can create a vacuum with, gravity is still taking place in there. You're not eliminating that force with vacuum, right?
Sure.
And you're going to be doing an awful lot of work to just generate a vacuum. It's not going to help you simulate microgravity as long as we're on the Earth. You know, gravity is pervasive everywhere, even in space, right? It's just the amount of force that it exerts. So,
yeah.
So,
go
I
ahead.
see one of your, so this one kind of reminds me of like a jelly jar, where you've got a cap and all you'd be doing is making your plunger to go inside. And I'm just thinking that that might be an easy way to start off with your prototyping, is to, you know, just take a jelly jar and see if you can get some stuff working with it. On your four-sided, you know, when I play here at home, I'll throw dice and I'll get one of them falls off the table, or, you know, it does something that I didn't expect. And so I just re-roll the dice. And so if I think the same thing will happen for the astronauts. If they get a four-sided die that goes off in the wrong direction, they'll just, you know, they'll redo it is all. So I don't think it's something that you have to spend a lot of time on, but it's certainly worth some effort thinking about what do we do to make sure that this is being consistently random. And so keep thinking on it, but realize that, you know, if it's just like at home, you can re-roll it and it's not that big of a deal.
Yeah.
I like your ideas. I think that keeping it as simple as you can is really important. Even that plus-sided plunger that you've got there, I think is still relatively simple, and it just keeps you from twisting and whatever. And I think that that's okay too. The other thing that we mentioned a little bit is just, you know, okay, so first of all, we're trying to keep randomness. Second of all, we have to engineer fun, which is really difficult, right? But then coming up with a style, whether it's, you know, making it like a dice tower that's transparent, or it looks like a castle, or it looks like a dragon, or it looks like a spacecraft, or, you know, come up with the style that you guys would want to play with when you were traveling to Mars. Put yourself in the position of what's going to make it more fun for you as the astronaut to want to use this particular dice rolling mechanism. Okay.
All right. Well, thank you so much. I appreciate your work on that. I like your designs very much. Really good presentation too.
Keep it up, guys. I like this a lot.
Yeah. Okay, so we're going to move to another dice team in the same city as this school is, in Bozeman High School. Thank you for waiting. We appreciate that.
Yeah. Can you guys hear us?
Yes.
Yes. Awesome. Cool. Yeah, that was no problem. We don't have much going on today, so yeah, no big deal. Let me get our slideshow up real quick. There we go. Is that working?
Yes.
Yes.
Awesome. All right. So we're from Bozeman High School. We decided to do the NASA HUNCH dice roller. I'm James Broderick.
I'm Olivia Gaylord.
I'm John Ryan. I'm Trent Sievertson.
So our other teammate, he's visiting colleges right now. It's that time of year. So yeah. Interesting. One second.
Just move that.
Oh yeah.
And you were listening to the last dice team, so
Yes.
that probably answered a lot of your questions too.
It was definitely a good thing for us to do. Yeah. So.
Yeah.
So as we said, we chose to work on the Micro G dice roller, and we connected with this because we find mental health really important. So we thought to solve this problem, we would give it a go and go through the engineering design process because dice don't work in zero gravity.
Done.
Some of the
How do I change my name? Oh,
some of the criteria and constraints of rolling dice for our dice roller is that it has to house at least 6 dice or like 6 different types of dice, and that it has to be reliable, randomized, and readable. So in the dice roller, we will have to keep like each roll has to be able to be randomized, and then when we're supposed to be able to see through the dice roller so that we can read the dice when they are held against the surface. Some of our research we did was on multipole magnets. We found multipole magnets to be the best because as there are more poles, it gets more randomized. And we connected this to refrigerator magnets. So we decided to possibly use those in our prototypes. And then we would make the dice made out of steel and the multipole magnets weak so that the dice can be overcome with force and therefore shaken or randomized and then pulled back down to be readable on the magnet. We also had to make sure that the magnets would not leave residual magnetized on the dice so that it would be usable for the next go around.
Okay, so after just doing some of this research on some of the magnets and stuff that we would want to go ahead and go to the brainstorming. Let me just get this Elmo up so we can show the brainstorming real quick. Oh no. Uh-oh.
We see your brainstorming slide.
Oh yeah, it's right there. There's just a little more on the yeah, there we go.
Okay.
So we came up with a few ideas. So in your guys' slideshow, we had the you guys had that shaker, right? So that's kind of the first idea we kind of wanted to just develop a little bit, just see how far we can go with it, just theoretically. So we came up with a few different shapes. So with the shaker, obviously we would have to be able to take it apart to access the dice inside, and we would have them, you know, a slightly magnetic one side, but like only slightly magnetic, so it can be overcome when you're shaking it. And we thought we would put like some stuff on the inside to randomize. That's kind of what this shows, just to increase that randomization that is so needed for dice. And then another idea that we came up with while we were just kind of looking at like dice rollers that are on Earth is actually the, do you guys know the board game Trouble?
Mm-hmm. Yep.
You guys, yeah. Okay. So you know how it has that little pop-o-matic in the middle?
Mm-hmm.
So it has like a little cricket spring right there and then the dome, and you just kind of push it up and down and the dice kind of get, you know, they get shaken around and randomized and then they come back down. So we thought this would be a good idea, especially if we could like make the spring like magnetized or just something like magnetize this base part so that when we press it, the dice are shot up, but then in the 0G, they're attracted back down to the bottom to the spring where they will, you know, be randomized and in random numbers. And we thought this was kind of the best idea that we had. So we decided to just develop this, you know, make a few prototypes of it. And so, what? Yeah. Oh, sorry, one second. Three. So that led us to trying. So obviously this cricket spring that we had was a little complicated. So we kind of wanted to find a patent for the cricket spring just to see how it works, like what the material is made out of. So we found something very similar to this Pop-O-Matic on the website Geekify, and we decided to contact them. And they actually responded and they gave us the patent to the Trouble board game, which was kind of interesting to get. And so with that, we got to learn a lot about the spring. As John will mention in the next slide, it's made out of spring steel. It really helped with kind of our design process of reverse engineering this Pop-O-Matic. So back and forth. Okay, there we go.
Yeah, so this cricket spring is the main and only driving force of the Pop-O-Matic. And to make it or fabricate it ourselves, we bought 2 sheets of 20 by 6 by 0.6 millimeter spring steel. And we're just currently researching how to make the spring. We have a few ideas currently, which are either A, heating up the metal and forging it, or B, cutting it and welding it and fabricating it that way. And we are kind of set on trying to fabricate it that way and weld it, just so that it could be cleaner and have a finished product by the end of the month, hopefully. Like they touched on, we want to add a magnet to the bottom of the spring so it loosely pulls the steel dice back down to the magnet. And that just, yeah.
Our first prototype of the dome aspect of our project is more of a simplistic idea of just catting the dome with a base, leaving room for the cricket spring once that could actually get created. Our hope for this one was to figure out the process of actually 3D printing, as well as testing out the ability to put the dome onto the base by a rail system of sliding it in and out. Our main issues with this was when we 3D printed it using the resin printer, the dome aspect, we put the supports on the inside, which made it extremely difficult to remove and really not smooth, making it really hard to see inside of it. So in the future, going forward, replacing our supports on the outside would be better for 3D printing using the resin printer. Also, we found problems with the rail system in putting the dice in the dome and then sliding it on, with having the dice stay inside of the dome. We thought that it would be inefficient, as the dice would not stay in the dome as well.
Get pulled off.
Yeah.
Yeah, they would just get pulled off pretty much and just kind of float away. So we decided to go to a different prototype. 1 second. Let's go back to this one and then boom, and then boom. There we go.
Yeah, and so for prototype 2, what we did was separate the 2 pieces into a base piece and a dome piece. And the reason for doing this is to get those dice in and out easier. And with this prototype, we didn't CAD or make one, but we would like to create a housing to house all the spring and the dome and all that, just so it's one big assembly and it's not too bulky or anything. And some of the problems on this prototype were the threads themselves. We couldn't get them to actually thread. The top part was a little bit too big. I think it was almost exact to the bottom piece. And so for our next prototype, we CAD'd that to be smaller and also to have less threads, so it would be harder to actually catch on those threads, and so it could actually like screw on.
Yeah.
So for our third prototype, as John touched on, we decided to cut down the size of it in half just for the testing of it to save materials and time with 3D printing it. However, by that process of cutting it in half, the material got super thin and fractured immediately during the process, cutting it and taking out a chunk when we took it out of the machine. So that was another failure we had with the 3D printing, which we now understand and have the ability to try and fix in the future.
Yeah, that's about it. Yeah, so whoops. Yeah, that's about it for prototype 3. We're working on a 4th prototype right now. A lot of kids have been using our printers, so we're working on getting that done. And so looking forward, once we get this figured out, we're gonna have to test and evaluate it. So first off, we were just gonna test it simply with gravity, just to make sure that it does have randomization on Earth. And then actually in a conversation with Flo that we had, she told us that we could like hold it upside down or sideways, just so that we could like verify that the magnet has the force necessary to like attract the dice back into the base. And then so we also researched some other ways to like imitate 0G. We found that plane that costs like an unholy amount of money. So we decided that probably wasn't the best idea. And then we also researched neutral buoyancy, which we found in that like NASA has a lab there. And we just kind of thought that this, like, it wouldn't really work that well with the dice. And it could start to get really complicated just with all that. So yeah, we're working on prototype 4 right now. We just need some printer space. We're really confident that this will work. And also in that same conversation with Flo, she told us about the 3D printer on the space station. And so the way we're making this is that it's entirely 3D printable, except for the cricket spring. So like, you could just print it on the space station and then send up a cricket spring, which is like, really small and doesn't take up a lot of room. And yeah, so yeah, that's about it for our presentation, I would say.
Very good. I do have a question. So you had you're doing threads, which, as you say, threads can be very complicated when you're doing 3D printing. Had you thought about like just kind of a twist lock instead of threading?
That actually hadn't crossed our mind. That's a good idea. Yeah, no, because that's a really simple way to take it on and off. Definitely would keep ease of use. That's a good idea. We could definitely look into that.
Okay, and not a requirement, just something that might help out with some of the mechanics. Now you're looking at using a spring steel. I'm wondering if you can put some compression or tension onto a piece of plastic and get a similar kind of springiness out of it. I don't know if that might save you from cutting spring steel can be difficult.
Yeah, we definitely found that through researching spring steel. John is our local metals expert.
You go, buddy.
Giving it a shot. But plastic could be a good idea. And then if we did,
and it would have a slightly different kind of shape, but you might be able to get a similar kind of effect out of like a small sheet of plastic and be able to press it in a direction that you're wanting. So just some thoughts that might help out with the mechanics there. Okay. And so another thought, I like the dome idea. It does seem to work pretty well. I can't think of anything that's easy to find that's like a transparent dome. That's not something that we get a lot of. Does it have to be semi-spherical, or could it have another shape? And what I'm thinking of is like imagine if I take my spring steel or plastic spring or whatever, and I put it in the cap of a jelly jar. Could you make it so that as you push down on the jar, could you get it to do some of that same kind of springy pop thing?
Yeah, if it doesn't like have to be like just a complete like dome. Yeah. Yeah, we've definitely ran into that problem. We were also thinking like, if it's easy to take off with just that like push and then like twist and lock, like you could just pretty easily just take it off and look at the dice. But I think it would be better to have it clear just to get that satisfaction of seeing the dice roll.
I think transparent is really important because it shows that there's nothing that is making it non-random, right? I think that transparency helps you feel like everything I'm doing is above board, right? Okay, I was just thinking about like some of the when I get those mugs with soda or whatever, sometimes they have a cap that's kind of dome shaped.
Yeah.
Do you know what I'm talking about? Not like a slushy, but if I get,
yeah, those.
You see what I'm thinking?
Yeah.
There might be something there to make it a little bit easier if you're looking for that kind of shape, and they come transparent sometimes. So you might look through your cabinet and see if you've got some leftover things like that might have similar kind of capability. So just some thoughts for you. I'll let everybody else talk too.
Yeah.
I'm really impressed by the work you guys did, and especially getting the getting the patent stuff for the Pop-O-Matic. I truly wonder, I'm a gamer. I truly wondered whether or not a team was actually going to go the Pop-O-Matic route, because I couldn't figure out a way quickly in my head of using it. But I'm really intrigued about where you're going with this. Keep up the good work, and I love all the iterations.
Thank you.
Awesome.
I'm just going to say the same thing. I thought of that exact mechanism as well. I'm not a gamer, but you know, I'm a parent, a grandparent, and yeah, Trouble has been a standard game for years. I like the whole idea of, you know, somehow mechanically or artificially, or however you want to put it, getting the dice moving, right? And inside that dome where you can see what's going on, that's just a very intriguing thing to me. So keep working on that.
Yeah.
Additionally, and you guys could start doing this now. I've mentioned this to other teams. We need subjective data, because this is a purely subjective. I mean, there's an objective part, right? You've got to establish the randomization, and you know, the variability of results is going to equal what we expect. So ultimately, whatever system you use, you got to do a lot of testing that way. But I just think finding out what people's, other people in your school, your families, get as many different subjects as you can to give you some feedback on their interest in what you're doing. I mean, that's crucial to this. If it's not engaging, if people don't want to do it, it can be as cool as possible, but it's not going to serve a purpose.
Mm-hmm.
Yeah.
Mm-hmm. But we know Trouble is very engaging to everyone.
Exactly.
Yeah. And we
So
have
there's-
some fun ideas to make it look pretty cool too. Like,
Yeah.
I think we could make it look like a castle or something. So yeah.
Something that you guys enjoy.
Yeah.
And I think that's a great place to start. I mean, whether you keep it as a dome, or you put, oh, okay. So I'm a big fan of Futurama, and so if you had if the top of it was the Planet Express spacecraft or something like that, there's all kinds of things that you could do with that.
Yeah.
So anyways, keep up the idea of how to make it. Engineering fun is complicated. I don't even know if it's possible, but that's kind of what we're trying to keep going here. So keep up with what you're doing. I like it.
Yeah. Thank you guys.
Thank you.
Thank you so much. Nice job presenting.
Thank you.
All right. So actually, I promised Mary in New Jersey that we would get to her class by 10 o'clock because they leave at 10:20. So I'm talking my time actually, but
Oh, okay.
so as long as we just see the Bozeman auger, but we have to cut it off a little before 10 o'clock.
Okay.
So Bozeman, you're still on?
So
Hi.
we had a bit of a snafu in scheduling apparently with this auger crew, because one of them is at Academic Olympics, which is not in Bozeman, so he's not here today. And then his partner
no.
is homesick. So
Oh,
you guys are.
So we can get to Mary Ann on time.
Yeah,
And
so-
we can, on December 5th, we're going to meet again, so we can have them present then,
Okay.
if that's all right.
Yeah, absolutely. I am going to give them a little bit of the fear factor of missing, since they did not communicate any of this with me. So I'm going to tell them they missed it to start, and then have them contact you to see if there's anything that they can do differently.
You bet.
So, just
Good
knowing
idea.
these two, it's like that would be a good learning experience for them. So
Yeah. Well, thank you. But
but I think we're back on with my collapsible mirror in about an hour and a half, or excuse me, 45 minutes, something like that.
Yep. Yeah, I see that. Yeah, at 11:30 our time.
Perfect.
Okay. Thank
Yeah,
you
so I'll see you in a bit.
so much.
Yeah, thank you, guys.
Okay. And then we can go right to Mary Ann then in New Jersey. Thank you
Hello,
for waiting. I was so glad that you text me to make sure I get you in on time. That was the right procedure. Thank
I
you.
just want to make sure because I have the kids till 12:20. So
Yeah,
I feel
yeah.
comfortable with all the other ones, and I know how things get shut. Let me ask you one other question though. The December 5th one, that's the same thing as this. We're not coming on again December 5th, are we? For
No.
another review? No,
No.
separate thing. Just
Yeah, it's-
another. could have done
It's more teams that I have, actually.
it. Okay, I just want to make sure. All right, that's my lunar field team now.
Awesome.
All right, good morning. How's everyone?
Good morning. Good. How are you guys doing?
We're doing all right. So
All
we're
right.
from the Technical Institute. My name is Marco Stefanacci. I'm the project leader.
My name is Adam Hamda. I'm the lead designer.
And I'm Veronica Montero Sanchez, and I'm the head researcher and technical drawer.
And we chose to design the lunar scooter wheel.
Yeah.
So first off, I'm just going to show you guys our brochure. We're going to go over the key aspects that we had to design around. Okay. So here's our criteria. So we had to make sure that the whole design could withstand temperatures from -280 degrees to 260, because that's the temperatures on the moon. We also had to make sure that it was durable enough to withstand, to hold 100 pounds of earth weight. And of course, it had to be able to move the astronauts around at approximately 1 meter per second. And of course, we have the measurement.
We don't see your PowerPoint if we're supposed to. But you're doing a good job. I didn't want to interrupt it. There, now we
Sorry.
got it. Now we got
Alright,
it.
sorry about that. So
That's okay.
here are criteria that we had to design around. So we have the temperature aspect, we had the durability, it had to be able to transport the astronaut around at this speed, and we had the measurements. And so we took all this into account, and the way that we split the work up amongst our entire class was we decided to start off with every student coming up with ideas, coming up with potential materials, just a very basic overview of everything. And once we got down with that, once we got our main ideas down, we started asking everyone to research tread designs, research rim designs, to potentially come up with a main idea that we would, I guess, turn into our idea. I know. Where should we go? Wanna go design?
Yeah. So this is our prototype of our lunar wheel. So the moon has very sandy and rocky terrain. So we wanted to make a hybrid between like a winter tire and almost like a sand tire.
So we don't see the prototype. We're still on the first slide.
Get rid of the PowerPoint.
Yeah, get rid of the PowerPoint.
Okay, you with me?
Do you see us?
Nope. PowerPoint kind of scooted to the side, but now we see you.
Okay, perfect. So we wanted to, okay, 1 second. So we wanted to make a hybrid between, for the tread, between a winter tire and a sand tire. So due to the terrain on the moon, it's very sandy and rocky. So are you able to see?
Yes. Nice.
So as you see in the middle of our tire, we have the tread design of almost like a sand tire. And then we have this very deep tread over here, more like a winter tire would go over a lot of the rocks. So we split up our tire into 3 parts. So I just went over the tread, and now we're to the main part. So as you can see, our tire is non-pneumatic, which means it's non-puncturable. We saw a bunch of non-puncturable designs online, and we gave it all to our students, and we all came up with ideas. So at the end, we ended up making these fin-like design, and due to it having so much of the fin-like designs in there, is over time is going to build up dirt, due to it going over sands, things like that, things of that sort. So we came up with an internal design for our tire. There's hexagons. These take off most of the bulk of the tire, which will help with reducing the cost, bringing it up to space. And this also helps with the dirt buildup. So let's say the tire is being used and it's rotating, and the dirt's going to build up in between here. It's going to all go through this hexagon. This is only a half view of it. So this is the intersection. There would be another piece coming over here, but this is the hexagon design will help with our buildup of dirt. And as the fins rotate, it's going to be blowing out all the dirt constantly from the hexagons, which will help with maintenance because we won't need a lot of maintenance, and we won't need to re-clean, do all these things for the tire to work. And then my classmate Veronica is going to talk about the third part, which is the rim.
Yeah, the rim. So we ended up starting off with a couple different designs. So as you can see here, this was one of the original designs. We did a lot of research going online, and we looked at common rim tires, ATV type of rims, and basically anything to give us like a main idea. And we ended up coming up with this one, which it may look like a simple design, but simple works best. So we were going to do arcs, but then we realized that when there's a lot of like ridges inside the rim, it can be kind of costly. So we ended up doing just plain circles. And then in addition to that, we ended up adding on beadlock rims, like as like a potential like inspiration. So with the beadlock, it helps ensure that the tire won't slip off of the rim, and it keeps it in shape and also very durable. And that goes on to with our like materials, which I'll bring that up like right now. Okay. Can you see it or no?
Not yet.
Not yet.
Here, Mike. Okay.
It's coming up. The PowerPoint we see now.
Yes. The materials. So with the rim, we were looking at a lot of different materials, including aluminum alloy and then obviously plain aluminum. And when we were doing the research, we looked at the old Lunar Rovers, and then we ended up doing like kind of like a compare and contrast between the two. And we ended up choosing aluminum since it's, I believe, 3 times stronger than normal aluminum alloy. And it's actually a lot, it weighs less too. And then with the rubber for the normal tread of like the wheel. And then we also were going to do like a mixture of silicone, since it reaches like the temperatures that we needed to hit. And for the prototype, the 3D drawing, Marco, he's the one who printed it out.
Okay, well, first of all, I just want to clarify our design. Let me switch to camera here. One moment.
Go ahead, stop sharing top right there.
Okay, so for our design, the basic, I guess, point of design is to have a flexible tread, unlike the standard, I guess, other tires that you have. So basically, our tread is going to flex over those, I guess, bigger rocks and stuff like that, along with that tread design of the straight lines guiding it through the terrain, just like a sand tire would. And then the aggressive off-road style tread on the side to really dig through that other smaller rocks and smaller sand. And we really wanted to go with the puncture-proof design to prevent potential leaks of, let's say we have gas-filled pneumatics. We want to prevent having to maintain really a lot of aspects of the tread. And so as for 3D printing, this is printed in ABS on our Stratasys 3D printer. And we wanted a prototype just so that we could be able to see what we needed to further develop. And so we could get a tangible object. And what else should be?
I mean, throughout the whole process, it was pretty interesting, like working together and really combining ideas, especially with the research aspect of it, because that's probably one of the most important aspects. And when it came to the actual CAD drawing, it was a little difficult trying to figure out how to, I guess, composite it as a whole, but it really came together quite nicely. And I hope that reflects with the prototype that we had.
Yeah.
Oh, it definitely does. I'm really impressed with that prototype. And we could see the details of it, which was really good. You did a tremendous job researching it. and then designing it. And then I don't even know how you could 3D print that. It looks so awesome.
Well, and I really like your design as well. I think there's some really interesting aspects to it. As you're so right now, it seems easy to 3D print it, but you've got different materials in there. How do you plan to construct something that represents it? What kind of other what's your next step in a prototype?
Okay, so our next step is we have a machine shop in our school. So we were gonna ask the kids there to use some, if they have aluminum or some other lightweight metal, they're gonna, I guess, machine this, the initial rim right here.
Okay.
And then, so once we have that done, they're also gonna print out the, machine out the beadlock little ring so that the beadlock design works. And then as for the tread, which is probably one of the harder parts, I'm gonna see if we can print that in some sort of flexible material, like a what is it? TPU, I know, is a flexible 3D printing material, which that would give us that flexible tread that we're really after. And we can adjust the infill of that to give us, you know, a less flex, more flex, however we see fit. And then with that, we'll go through.
Okay, and so on the flight design, the one that would go to the moon, you're suggesting that the silicone would be the material that would be flexible for that kind of temperature range?
Yeah, it would be some sort of a silicone composite. We're still, like, I guess, narrowing down our options, but a silicone composite that would withstand the temperatures would be perfect for this design because it would give us that flex, but it'd also be durable enough to withstand the harsh conditions.
Okay, and you can simulate some of that with just some silicon caulking kind of stuff. It's not exactly the same, but there's a lot of similarities to it.
We can also make a basic mold and pour that in, let it dry, and then we'll mount it up to the rim.
Okay. Well, and remember, so one of our biggest difficulties is just that temperature range that we're talking about. I mean, this is, you know, that's a 500-degree temperature change. That's kind of significant. So so keep that in mind and look up your materials to see how they're going to behave at those especially at the low temperatures, right? We're not going to have now you had said pneumatics, but I don't think you were talking about air being in there. You're just kind of simulating it, right? Yeah.
Well, we're doing a non-pneumatic design with the puncture-proof aspect.
Right. And so also the other thing is make sure you're thinking about those weights. Now with your 3D, what's your CAD system you're using?
We're using Autodesk Inventor.
Okay, and that's fine. And so in there, you can also determine what the mass is by using choosing the materials and then adding up the mass. Make sure that you're looking at something that's going to be keeping it as lightweight as possible. Okay?
Okay.
Keep going, team. I like the way you guys are working this.
Thank you.
Thank you.
Thank you.
Yeah, you know, the silicon, I think we all know that silicon is pretty resilient, especially at high temperatures. They're using it now for a lot of cooking materials. So I don't think that that's the issue. But doing some research on how this stuff fares at temperatures that are hitting, you know, hundreds of degrees below 0 Fahrenheit, that's a wide range.
One thing I wanted to add, and Glenn covered almost everything here. I may have misheard this. Your fins that you had you said when they rotate would blow out the dust. Is that what you said, or?
Okay. The fin design, you can see that was the main aspect of that. Well, originally we started with the fin design as our flexible puncture-proof design, but then we realized that the sort of hexagonal shapes give a lot more resolution in the flex, if you understand what I'm, yeah. And then, so now we decided to go back with the fin design, but as sort of a dust cover, so that the debris doesn't build up inside of our design in the back.
Well, that was okay. That was one of the things I was thinking about is I'm thinking about my own truck, where I have brake dust. I was just looking at this, all like just totally covering the outside of that, and you're creating a lot more surface area for that dust to grab onto. So be careful when you go that route. Okay.
Okay. And each of you represent a whole team. We want to recognize, because this is an entire class. So
okay.
we want to recognize the other students
Okay,
in your team.
So our materials people, say hello.
Hi, materials people.
Very
All right,
good.
and then our researchers.
Researchers.
One of them is, but listen.
Very
And
good.
then we have,
Good
So there's
job.
only two waving at me there.
and then we have our design folks.
This is
Uh-huh.
Johnny.
Wow.
Design.
We designed the tire.
And a lot of us were working on the CAD, helping each other out. So that was a big part of it.
Excellent.
Mhm.
Yeah. So everyone really did put in their effort.
It's
And are you-
obvious you guys put a lot of work into this.
Yeah,
Yes,
it,
it is.
it really is. I'm really impressed with the design. And are you all seniors then?
Yes, we are.
Yeah, we are.
Yeah,
Very
awesome.
good.
Awesome.
Hey.
And the shop will be more than happy to help you, I'm sure, because they already work for us also.
I had one more question. Gene, you brought up some really good points there. Is there a reason that you chose the number of hold up your wheel again? Okay. And so on the outside there, you've got the little ridges that the dust is going to blow out of. Is there a reason for the spacing or the number of those that you've
So-
chosen there?
The spacing right now, as it sits, we didn't do a whole lot of research, but the spacing is going to be based off of the average material of the smaller debris that could get stuck into our design. So we're probably going to go like, we're going to make it so that that material doesn't get stuck, but also if there's the smaller sand, that will push out.
Okay, and that sounds
So-
good. And so as you scale this up to the closer to the full size, did you guys have a plan for how you were going to do some testing?
So our testing, we're going to create maybe like a representation of the lunar surface we're going to take we're going to research measurements of the average size of the different materials. And of course, like the astronaut will be steering the scooter, so we're not going to be dealing with massive boulders and stuff like that. So we're going to
And
make,
that's exactly right.
yeah. So we're going to make a
So-
simulation.
And so just a suggestion, look for some fairly fine grained sand, not play sand. You might mix a little bit of play sand into it, but we're going to be dealing with a lot of very fine sand, and then put some rocks in there that are, I don't know, size of a silver dollar or something like that kind of thing. Because like you say, yeah, they're going to steer around big rocks. Now, I also noticed that you have it, that there's a crown on your tire, meaning that it's rounded, which I think is also very wise. Just like most, a motorcycle tire is significantly different from a car tire in terms of its
Yeah.
flatness,
Yeah.
right? And so I think that that's also very smart. I like the way that you've got your tread so that there's a central ridge as well as some grip on the side. That's very
Yeah.
similar to the kind of tires I chose for my bike, where I've got kind of a ridge, and then if I get into sand, then it starts sinking down, and then I've got some extra traction. So I
Yeah.
think that you guys are going in a good direction. I like that a lot.
Thank you.
One more question. I see that you've got there's a place for the axle. Did you guys have a plan for some for bearings?
Okay, so the bearings, we haven't done a lot of research on that yet, but that is all to come.
Okay, very good. And I mean, you're going to be looking for like a sealed bearing so that the dust doesn't get into it.
Yeah.
But start planning for how that's going to fit into that hub area. Okay.
And there might be some bags of sand at your school, because we have the critical design reviews there. And one year it was involving wheels. And I know Mike Kasha bought a lot of sand there. He had like a kids, I don't know if you remember that, Glenn, but they had a setup for testing. So
Oh,
they
is that
might
right?
have, yeah. So they might have something that already you can, I think they had like a kids pool or something and they put a bunch of sand in. So see what's there. That was before COVID. So it's been quite a while, but you also have the beach. So you can get a lot of sand in New Jersey. So cool.
All right.
Really nice. Very impressive. Great job presenting too.
Excellent job, team. Class, I'm very impressed. I think you guys are all working on a good project. You know, whenever HUNCH is developing something, we're working with several people that are all doing different jobs to do this same kind of thing. So I think you're getting some good experience on working on a team and working on a project together. So excellent job. Keep it up.
Did you have any questions for us before we?
So, question, if we make the finals, would the prototype need to be a life-size prototype? Like,
If possible.
The wheel?
If possible. And just as I was talking with you, I was thinking about how I need to develop it like a yoke so that we could slide. If I bring along a 1/2-inch piece of steel or diameter, we could slide it through and be able to have students, you know, test it out a little bit somehow. Initially, I had thought that it'd be nice for me to bring around a like a scooter and have everybody put their wheels onto a scooter and we could push it around. But I think that might be a little bit of effort for me to take it from city to city. So, but I think that I could definitely take a big yoke so that we could put it into the sand and push it around a little bit. So let me see what I can do for that.
No, this guy is the NASA engineer. See that behind him?
Any other
Okay.
question?
Not, well, we do have something else. We have a few other mock-ups of design drawings and everything like that. So I'm just going to show you guys real quick. Let me just share my screen.
Hi, Scott. You're going to be up next.
Okay, thank you.
Okay.
Yep, thank you.
We don't interrupt if they can hear us.
Yeah, you got to mute yourself.
All right, so here we have the design drawing of the rim, everything. So we have our final dimensions, which is one of the main parts we want to talk about. So for example, you can see here, this is a 7-inch, well, about 7-inch rim from edge to edge. Because we felt that we were looking at sizes of, I guess we were also looking at previous lunar scooters and lunar rovers, and we found that this size was best suited for what we wanted to purpose the wheel.
I'm not sure dimensions is. I'm not sure I quite follow what I'm looking at there.
Oh, okay, sorry. So here we have the front view of the rim itself.
Yep.
Yep. This is the backside view. We have the bead lock on only one edge because that's typically how it's done also in the off-roading industry.
Okay, keep going.
And here's the side view.
Oh, I see. Okay.
So your total width of the rim is like 6 point whatever, is that 6.9?
Yes.
Yeah,
Okay.
it's in
Okay.
adding on like with
Got
the
it.
bead lock
Got it.
on the side view as well. Here, wait. Here,
Let me stop.
because the bead lock sticks out a little bit, so I added it into the whole width of the rim.
Okay.
So that's why it might be just
Got
a
it.
little mix.
Okay.
But yeah, as for like the standard size of like the width itself of the rim, I just looked up standard ones for the Rovers and normal cars too. So that's why it might be that long.
Right. And I don't know a lot about the bead locks, though. If I'm thinking about them on a Jeep, so if I look at the rim, I would guess that the inside of the rim, the inside side of the rim is probably taller than the outside of the rim. Is that correct? Okay, and that's why you only have to do one of them. Okay, and that makes sense. It just makes it easier to put on the tire, and then you lock it into place with that bead.
Yeah. Yep.
Okay. Very good. Okay, thank you so much. I appreciate that.
Okay, well, thank you, team. And you'll have one other team present at the end of the day, 2 o'clock. So.
All right, thank you very much.
Thank you.
Thank you. Have a good lunch.
You as well.
Thanks a lot, team. Good job.
All right, Scott, we're ready for you guys when you're ready.
Okay, let's get our stuff up. Share our screen.
So we're back in Wyoming now, and this will be the
wrong one.
Auger team.
I got the wrong one. Who's that?
Oh, you got the soft goods one.
Yeah, I got the wrong one on here.
That's okay.
Okay. You guys want to introduce yourselves? Go.
Yep, we see it.
All right. Get your mask.
Put it in
I
slide presentation mode, slideshow.
Yes, I'm Kieran. My name's Anthony. My name's Aiden. And we're doing the slideshow presentation for the pipe, auger, and extruder.
Awesome.
So this is the cover. So our project is trying to figure out how the pipe, auger, and extruder is going to work on the rover, the Lunar Rover. And we are trying to figure out the constraints and the problems we have to fix with this. And we are figuring out our extruder and how it will shape our bricks, and how the bricks will come from the plastic and the soil and mix together to form a plastic brick that will take up, it will fix the problem with the trash in space and on the moon. And okay. The problem constraints is the edges should be rounded for the auger, so it's easier to mix and pick it up and push through the extruder. The advantages for the brick is to emerge. How do I move this, Scott? How do I move that? On the bottom. Okay. The less plastic required to hold the sand together will be with greater compression that is applied to the brick during the cooling phase. There is no flow of air to help cool the brick because it is in the cooling vacuum of the moon. Only the brick's contact with the channel or holding the bin and its radiation into space may do this. The ideas is for our prototype, we're going to use a clear pipe to show what so for our prototype, when we use the auger and the clear pipe, it will show us what's going on within the pipe, but the clear pipe isn't like the final material we're going to use. So take off there. And the extruder, we're going to be using a meat grinder for the prototype to help us find an idea for extruding and all that. And brainstorming, these are our different prototypes we've came up with just on how we're gonna build the prototype to see how it's gonna work. I think that's my last slide, I think, yeah.
Hey guys, let me make a couple of quick comments. This is very creative. I like the idea that you've come up with of at least starting out with a clear tube You're the only people I've known that have thought about that. It's going to be very useful to visualize what's going on inside of this thing while you're mixing and extruding. So obviously that's not a, not a final version, but I like what you've come up with there. That's brilliant. I also like your meat grinder.
Yeah, I like that.
I mean, that's smart. That's really a very creative way of going about this.
Well, and a meat grinder can handle all of the temperatures that we're talking about. So you guys could come up with ways to warm that up and be able to start off. And this is a suggestion for you. You can start with like candle wax, mixing candle wax with your sand, and then later on, after you get some experience with a low temperature, then you can go to high temperature and look at the plastic. So I like what you're doing. I think this is very smart. Good job, team.
I agree. I think I'm impressed. This is nice.
Very interesting. I like it.
And another thought, I made this comment to a couple of teams earlier. There has been so much focus on the auger itself, right? And moving this mixture through it to extrude. I think it's equally important to back up and think about the mixing of these ingredients and the process that we're going through, right? My sense is it's going to make it's going to probably be best if you can take the plastic and somehow shred this up, grind it up into something that is, almost a powder or particulate in nature, mix it with the regolith in a dry sense, right? Just like if you're throwing, flour and sugar, et cetera, to bake, and you mix all those dry ingredients to get a nice homogeneous mixture. And then you can heat this stuff so that the plastic melts and you get the consistency you want. But we've got to be thinking about, the ratios, the ingredients itself, right? So you've come up with some really innovative ways of addressing the mixture in the auger. Take a step back and think about what you can do to combine these things together in a way that's going to be most efficient to get a nice, evenly mixed composition. Okay.
So I'm not as familiar with the meat grinder, but before it goes into the auger, that part on the top of the meat grinder, is that for mixing the ingredients that are going into the meat grinder?
So in the second picture, we have the plastic, what's going to hold the plastic material, and hopefully underneath the auger is going to be somehow going to collect the soil, and they're both going to go to the bottom of the auger, and hopefully they're both going to mix, and with the mirrors around the pipe, it should melt it. And while it's going through the auger, it should mix. And then on top, the extruder is going to be there to push out the brick and form it into the tray.
Well, with your meat grinder, I think you're going to be putting both of your two constituents into that top hopper, right? And so, and I think that's a good way to mix them. I'm not sure how we're going to do it on the Rover yet, but your idea of or using that meat grinder, I think that's the way that we should start off with your mixing. Because I think that's a good way to merge the two together.
Right.
And Dave's exactly right. In terms of those particulate, the smaller you can get the plastic particulates, the better. I think that we're probably looking like, if I took a milk jug and kind of cut it up into small pieces that are like, when I was a kid, we used to have chiclets, right? It was the little pieces of gum. That would probably be pretty good. I don't know. Do you guys have some kind of a...
Here's a thought just came to my mind. and we haven't really looked at this, but you know, all of this plastic that is going into recycle centers now, what are they doing with that? Right? I mean, you know, like Glenn said, you've got a milk jug, you've got plastic grocery bags, etc. I think it's worthwhile doing some research and seeing the methods they're using now to kind of regrind this stuff into something that they can make another plastic something out of, right?
Yeah.
Because again, why reinvent the wheel? Let's find out what mechanisms are currently being used in this fashion. Now, that doesn't mean you have to incorporate that into what you're doing, but I do think it's an important part of this whole process, right? We're going to have to find some way to take different types of plastic and essentially shred them up, grind them up, pulverize them somehow so that they can be mixed, right? So do a little research there. I imagine there's a lot of information online that would help us out with this whole project.
And if you look at buying plastic by way of the way they use it, they typically come in little tiny pieces. They're probably like about maybe 3 millimeters on a side, so that they're really tiny little beads, and that might be similar to the kind of size that we're looking at.
Yeah.
What do you call?
So you could
I'm
get
trying to think of a
plastic
candy.
beads. They sell plastic beads.
They do sell plastic beads, but I mean, if you're going to take a milk jug, which I think is a free and cheap way to get the kind of plastic that we're looking for, you could cut that up into some pretty small pieces and be able to have a good simulant for what we might be doing on the moon.
All right.
Do you already have a meat grinder that you're going to work with?
Yes, we haven't put
Oh.
together the prototype, but
Let me see.
Could
Stop
you-
sharing and show
Yes,
us.
stop sharing.
how do I?
Run your cursor at the bottom of the screen. There you go. You stopped.
Okay.
Done.
All right. So we got the clear PVC and then somewhat of an auger.
Yeah.
So we're gonna something like this.
Yeah. Very good. I think that's terrific. Okay, so you've got the auger, but you don't have the meat grinder yet. Is that right?
Yeah. Not yet.
Okay.
Just-
No,
just-
I think that's exciting.
Just a point, I was thinking about this when you were saying that you were going to use a transparent tube. Is most transparent plastics or materials are very they scratch a lot. So be aware that that's going to become cloudy very quickly once you start using it.
Sure. No,
And
he's right.
use two different colored things to mix so we can see how well they mix. So if you're using sand, you color some of your sand, or if you can get some beads and sand, different colors though.
Well, yeah. If you start off with the candle wax, use like a red candle wax to mix with your sand, and that'll give you a good idea as to how well it mixes first. Okay.
All right.
Excellent. I'm really excited to see what you've got there. I look forward to this. I think that's a great idea that you've got it. Hold up your auger again. Let me see that. Okay. And so, do you have a plan for how you want to connect up the handle to this thing, or how did you want to work it?
Yeah, that's what I was thinking. We can probably use the meat grinder handle to work this while we can watch it mix. So.
I think that's exactly right. I think this is really smart thinking, team. Good job.
Awesome. Do you have any questions for us?
Not really. You kind of answered them for me.
Okay, great. Thank you
Very
so
good.
much. All right. So then, thank you, Scott.
Yes, thank you.
Did a great job. So that's all your teams. Did we get all your teams then?
Yes, we're good.
Awesome. Okay,
For this
thank
round.
you.
Yep.
All
Okay.
right. So Jackson Hole is next. They're doing solar tracking. So if you want to stay on, Scott, just mute yourself and you might want to hear Jackson Hole.
Okay.
Do we get a potty break anytime here, Flo?
I actually just took one, but I don't see Jackson Hole on yet. So it's a good time, actually.
Okay.
Because I don't see Jackson Hole yet. And they might not show up. Council Rock would be after Jackson Hole.
Whole bunch of solar tracking today because you guys were there. So I would watch Jackson. Jackson's usually, they're pretty up.
Yeah. But they're not on yet. So we got a little break. I'll see if. Let's see, I don't see Jackson Hole on yet, Scott. I don't have Keen's cell phone, but I do have Gary. Maybe he can.
How far are we behind schedule, Flo?
No, we're right on schedule,
Ah,
actually.
okay.
Jackson Hole is supposed to present at 10:30 my time, 12:30 your time.
Okay. Good.
But I don't see him. I'm just seeing if he emailed me. Oh boy, do I have a lot of emails here. Oh boy. All right, I'm gonna email Mr. Anderson.
Yeah, that's difficult for me too. So I've got, okay, what time are we done here today, Flo?
So 12 o'clock my time, I think, what, 12:30 my time, which would be 1:30 your time.
1:30. Okay. All right. Sounds good. Thank you.
Earlier done today, but we didn't get a break. Okay, so I just sent him a. Oh, wait, here they are. Hi,
Hello.
we're ready for you.
Awesome. Great.
Uh-huh.
How is this gonna work, if you don't mind me asking?
So, you just have to share your screen if you have a PowerPoint or anything, but if not, we'll get to see you.
Okay. Let me see if I can. Wait, how do I hide?
Hide from controls. No hide from.
Okay. Okay.
We see you.
Great.
Awesome.
Okay.
All right. Is it okay if we start?
Yes, we're ready for you.
Awesome.
So we are the solar tracking unit designed by students group. I'm Peyton Harris.
I'm June Darren.
We're from Jackson Hole High School, and we're in Mr. Anderson's engineering class. So the problem was to effectively collect and utilize solar energy on the moon. Solar tracking systems would require mechanism and software to locate the sun and reposition itself to aim at the sun. Given the differences between solar light at the lunar South Pole and in normal conditions on Earth, this is an especially challenging task. And it must also be able to determine some of the other functions on the rover. So two of the things that we looked at were a dual axis solar tracker, which can be seen on the left here or on the right. And then the other one was the Rosa solar array that was on the ISS. And then some important info concerning solar tracking would be that some areas are in near constant darkness, while others are in near constant sunlight, which even makes the tasks more difficult. And then the other one is that the sun is usually really low above the horizon and it doesn't get very far up. So these are kind of the constraints that we came up with. Number one, it must be able to target effectively. Number two, the design should be simple. Number three, kind of goes along with that, durable. Number four was lightweight. Number five, it must be able to endure a high temperature range. And number six, it must be safe and easy to repair.
And the next part of our project was we took each of our brainstorming ideas and then we ranked them based on the criteria you saw in the prior slide. So what you're seeing right now is our decision matrix with every single mechanical related idea we had. So
See why.
hi.
Hey, sorry about that.
Oh, you're good. So we have eight mechanisms here that were ranked. The criteria we have is targeting effectiveness, which is weighted the most because that's the most important part of our project. Then simple, durable, lightweight, and safe/easy repairable. As you can see in this slide, the idea that came out on top was the dual axis tracker. Some other brainstorming ideas that were featured was just the horizontal axis or just the vertical axis or completely stationary. And we also included some out of the box ideas with a bunch of smaller solar panels mounted in many locations or having reflective surfaces on the rover to reflect into one solar panel, as well as doing a pre-calculated path based on the sun's movement and the fact that the rover is moving in a constant trajectory. And finally, the parabolic cone idea, which is focusing light on this panel. Next, this is our second decision matrix. It's smaller. These are our ideas relating to solar panels. So we have the rollout solar panel, which was inspired by the rollout solar array that Peyton talked about, featured on the ISS, which was ranked the least due to durability and how repairable we thought it was. But and we also had the fold up solar panel, thin film, and crystalline solar panels, which is just standard. When it comes to solar panels, we did end up picking crystalline solar panels, but we're still it's possible that we might end up doing a rollout solar array because we thought it would be better to make that final decision once we've done testing.
So these were kind of the pros and cons for each of the winning things from the solar panel and mechanical category. So a dual axis solar panel or a dual axis tracker we determined would be more versatile and more effective, but more complex and heavier. A crystalline solar panel is more efficient and works better in higher temperatures, and it has a longer lifespan. The cons would be that they're expensive and they're heavy. So this was kind of our CAD over here. So basically it consists of two parts, the vertical axis and the horizontal axis. Here on this side is the vertical axis. The solar panel spins along this shaft here. and it's spun by a motor that's just behind this panel here. And then June will explain the horizontal
Yes,
tracker.
so this is our horizontal tracker. We have a large gear that also doubles as our base plate that is going to be secured to the rover, so that will not be moving. And the motor, can you go back? As you can see, there's a motor with a little gear on the image to your left that will go around the circumference of that gear. And then to go back to the next one, and then we have a bearing inside, which is what our entire assembly will be attached to, so it can spin freely.
Next, we kind of just worked through some of the logic that would be required for this solar tracker. So we have a little chart over here. Basically, we work through, do we have a target? Is it the sun? And then we rotate to the correct pitch and yaw that we get from our sensors. If we don't, then we kind of work through how do we find that target and then get through here. And then this is just all looping. And then here's that written out in a kind of pseudocode way.
And finally, we have our next steps where we want to go with our project after we receive feedback and complete this review. So we want to get a physical prototype completed by early December so we can start testing and finalizing the size of the solar panel and the type of the solar panel that would be the best, and also beginning to work on our code. We do have our pseudocode, so but we want actual code ready. We also would like to redo some of our CAD. It's pretty heavy at the moment, so we would like to cut a lot of weight out of our mechanisms and make sure that it's very adjustable to different sizes of solar panels, which is one of our goals, as well as testing many types of our prototypes and just doing a lot of testing. And that's all we have in our slides. Are there any questions?
So have you built anything so far, or are you just looking at your CAD models?
We're just looking at our CAD model. We have not built anything yet.
Okay, and so I see your CAD models look pretty detailed, and it looks like a good plan. But what kind of things do you want to do as your first prototype? Do you have?
Ideally, if I just exit the slideshow here, I have the CAD up here. So ideally, our first prototype would just kind of be a recreation of this CAD, and then we kind of be beginning the testing process, and then determining from there what changes we would need to make.
Yeah, and before we move to our prototyping, we want to make sure our design is adjustable to size of solar panel, because that's one of the main things we're testing for, because we're not entirely sure what to do for that to maximize efficiency.
Well, and part of what I'm thinking is that, you know, a lot of this looks similar to a like VEX parts or some other components that you might be able to use to start off and see what things work best for you, rather than, I mean, don't expect that your first design is going to work exactly right. You might need to play with some of these concepts before you start building. I mean, each of those can look kind of complicated to machine. Does that make sense?
Yeah, we actually chose our parts based off of ones that we had in stock in our robotics team.
Excellent.
We tried to make it so we had to machine as little as possible.
Very good. So which components do you have there that are these off the shelf from something else?
There's a lot of things here that are off the shelf that we've used in our robotics lab. For example, these C-channel things here, and then motors. But we also, everything that we would have to machine, we made sure that we would have the capability to machine. So we have a fairly robust robotics lab here. So it would be not super difficult to machine things like this, which was designed with the idea of being machined.
It's still loading.
Take a second to load.
That's all right.
There we go. Yeah. So we have a CNC at the lab, so we were planning on cutting this out of either aluminum or polycarb.
Okay.
Probably polycarb or wood for our prototype. And yeah, so we're pretty well versed in the CNC, so we're not worried about that manufacturability.
Yep.
Okay. And I think that polycarbonate is a good way to start, just so that you're not spending the money and time on the aluminum. I think that's a good idea. I'll let some other people talk. You guys got thoughts?
I was going to say that, yeah, I agree with you, Glenn, that I don't think that they need to spend a lot of time and money to build all of this contraption when you have your major problem here is controlling that 2-axis turning, and it's going to be the software controlling the stepper motors most likely that you're going to use to turn that. So the quicker you can just build that, I mean, a round table with a gear on it is something that you can control with the stepper motor will get you a lot more forward than waiting for everything to be solidly built.
Yeah.
I'd start working on that software as soon as possible.
Yeah. So yeah, that's kind of our next biggest step as far as endeavors. And we're kind of thinking about using like absolute magnetic motors, which would give us pretty complete control over the exact movements of our mechanisms.
Yes.
What are you going to have you? And forgive me if I missed it in there, but what are you going to use to track the sun itself?
So we've kind of had two ideas there. The first would be a camera that essentially takes a picture of the sky, and then we're able to pick out kind of the brightest location. And then the other would be kind of an array of light sensors, which would tell us kind of where the brightest location would be, which is almost always the sun. But then we'd also have additional logic, which I can go back to our pseudocode here. We would have additional logic here that's basically says, should the sun be out, is this thing really the sun, which is based on our knowledge of kind of constants relating to the sun.
Okay, again, software it takes a long time to debug. So get on that as soon as possible.
But you're in the right step making that flow chart. That's the way to start that software.
Yes.
That's great.
So let me offer you guys a thought on this, because we want to keep this into perspective. There are a lot of free apps that you can use to, for instance, image the sky from the surface of the moon, right? Which will allow you then to look at the sun's position from any latitude over time. The key here is when you think about a solar panel that's capable of tracking, moving with the Earth's rotation to keep the sun in direct alignment, right? We're in a situation where, we've got maybe, let's just say arbitrarily, 12 hours from sunrise to sunset. And you're moving a panel close to 180 degrees, right? Mm-hmm. On the moon, that's not necessarily going to be the case. First of all, you've got a rotation that's 28 days, right? Mm-hmm. The moon is up for a very, very long period of time, and its motion across the sky is incredibly slow. So when you think about this whole contraption moving over the surface of the moon, let's say it's working for 8 or 10 hours, right? That sun is not really going to change position relative to the rover at all. I mean, like less than an arc degree, which means that you don't need to have this thing, moving in dramatic fashion as we would here on Earth, right? And that's going to make some difference in your coding, et cetera. It's going to simplify things if we put it in that context. So again, it would be worth looking at it. And there are all sorts of apps out there that you could just get to, say, take me to the moon and show me the night sky, or show me the sky. And then you can see what that's going to be like, right? And that's a good perspective to have, because again, one of the challenges we have with a lot of our projects is we're building for space. We think here on Earth, right? Our brain is programmed to think the way things are here. It's not going to be the same way on the moon, right? So get that perspective before you start, doing your programming, et cetera.
That's a really
Does that make sense?
That's a great point.
I mean, it's, we're not looking at having to dramatically shift these panels over, a few hours or a single day. They'll need to be adjusted. And of course, we want the flexibility of saying, well, what if we were to put this on the equator of the moon, or, 40 degrees north or south latitude, or, like the South Pole? Well, obviously, it's going to have to change. But
well, hold on a second. Hold on a second. It is a little bit different than that, because this is not a stationary, right?
Right.
So what's happening is it drives south and then it turns around and drives north.
Right.
And so that means that if the sun is over in the east and I'm driving south, as soon as I start turning and going north, I have to switch that panel a very large amount in a very short time.
Yeah.
So there is some of this, but but the point that you're making that's really important is that the sun is not changing all that much. The position of our rover is changing.
Yeah, that's true.
Now,
that's very true.
Now, another thing that we're forgetting here is that this is a solar panel. It's already a sensor, a solar sensor. So really, can you use the power that's coming off of the solar panel to help you direct it so that it's pointing at the right thing?
Mm-hmm.
So is that possible?
I mean, I think if you get the right solar panel, from what I've just kind of researched a little bit about solar panels, if you have the right solar panel, you could get like a voltage measurement from different portions of the solar panel. So that would definitely be an option to look at.
Well, but if they're all in a plane, they're all going to give you pretty much the same value. And so all I'm suggesting is you may not need to have a camera looking for the sun that's on a separate system. All you need to do is determine what value am I getting off of my solar panel and position it. And if it turns a little bit to the east and it gets higher, then I keep turning it to the east until I get to the highest value I've got. Maybe it goes a little bit past and then I come back to it. And so your solar panel can be your sun sensor.
Yeah,
that's a really interesting point. We'll have to do more research into that.
And that sounds good. Now, remember, the other bright thing in the sky is going to be the Earth, right? And so determining the difference between, my solar panel is pointed at the Earth as opposed to the solar panel being pointed at the sun, how to determine that, I don't know. And then you're also going to have the instance where the sun and the Earth are in a similar kind of location. So I think there's some other options here to look at.
That's where like imaging the entire sky would be useful, because almost always the sun would be the brightest object.
Sure.
Yep.
Sure.
And the camera might be good for that kind of situation. So you might need both. I would, and I love redundancy, and I love what you did. It showed you did a really nice job on researching and designing it. So I really appreciate that. Awesome. Okay.
Excellent job, team.
Yeah.
Thank you.
Now, another thing that might be able to help out a little bit is that if we're only going north and south with this rover, it kind of means that we don't need as much tilting from north to south, and that might save a little bit in terms of your gearing, so that you don't need as much of a rotation in that for those directions. Does that make sense?
Yeah.
Yeah, that would make sense.
And I don't know where they're going to make these bricks, right? I mean, are we at 30 degrees longitude, or excuse me, latitude, or are we, are we right on the equator? Probably not. And so that'll also affect that range of motion for north to south kind of thing. Okay.
Yep.
Excellent job, team. I like where you're going with this.
Yeah.
The fact that you have so much capability with your machining is going to make a huge difference. I'm very impressed. I didn't realize that you had that kind of capability. So I look forward to seeing what kind of things
Very
you guys
lucky to
develop.
have that.
Yeah, they have an amazing lab there. Gary Duquette is the one in charge of that. So yeah.
Well, there.
Amazing
That explains
lab.
a lot.
I've been
So
there. Yeah.
I'm jealous. I
Yeah.
don't have that kind of capability right now. So very
They
good.
do. Okay. Well, thank you so much.
Thank you all so
Thank you.
much. Take care.
Take care. Stay warm. All right. So now we're going to move to Pennsylvania to Mr. Bauer's class in Council Rock. Hi, guys. So you got a solar tracking also, team.
Yes, we do.
No plagiarism here.
Were you listening to the last team?
Yes, we were.
Okay, good.
I am Eva. I am the team lead.
I'm Jaden. I'm another member.
And then Jack C is also in the call. He is in North and is here somewhere.
So they incorporated kids in Council Rock High School North also, which is awesome.
Go.
So this is Solar Tracker. So our main ideas and our problems. So our problems were we have to track the sun and point solar panels at the sun. It has to be fast, efficient, and reliable so that we don't have to take it for maintenance or stop production for any reason. Our most ideas is Arduino controlled motors for the movements and light sensors to improve accuracy so that we have more accurate precision. So here's some concepts and ideas. Our main idea is a light sensing solar panels. So the solar panels are attached to opposite leads of a DC motor, which causes the motor to go in opposite directions depending on which side of the solar panel has the most light. Eventually it really reaches an equilibrium and it points where both sides are getting the most light. We do have a prototype printing on the 3D printers right now. I was not able to get it soon enough for this, but we do have a prototype being printed.
So the materials we'll need: a solar panel, obviously. We'll need a housing for all the inner electronic bits. We'll need a DC motor and an Arduino. And in the future, for an actual build, we would use a metal encasement to shield from radiation and other like mercury, and larger solar panels for increased power generation.
Other idea we threw around was a solar panel dome. So we didn't really have to worry about tracking when we just have a 360 dome full of solar panels.
It's like that, but small.
Yeah. So some future additions. Right now, we don't have a plan for our up and down movement. So we obviously in the future will want metal parts instead of plastic that can easily melt if it gets too hot with everything going on the Rover, and for it to be fully software controlled. For up and down movement, we do have a few ideas, mostly piston pointing up and angling it, but other than that, we don't really have any solid ideas or concepts. And that's it. Any questions?
Hey, team. Okay. So what kind of things have you already done? Some of your software? Have you already put together some of the motors? What do you got?
We have started on our software, and shipping is taking a while for everything else, and we have the stuff printing. So we have started on making our software, learning the software itself, because we don't really know it all that well.
Okay.
We've also started, printing the parts themselves and waiting on Amazon to get us the solar panels and the motor that we need.
Tell me about the parts that you're printing.
It's a base to hold everything down and a little plastic encasement for the motor and the solar panels so that they can sit there nicely and then rotate freely.
Oh, that sounds good. Do you have any of those things that we can see?
They're on the printer right now, unfortunately. I don't have any.
Oh, okay. I didn't know if you had like some CAD drawings or something that you could share.
I forgot to pull them up. I unfortunately do not have them.
Okay. All right. Well, and so so you're talking about just 2 motors, is that right? To be able to move this back and forth?
Most likely just 2 motors, one for the right and one for up and down.
Okay. Sounds good. Are these going to be are you going to need to gear them, or are they going to be strong enough to be able to rotate things the way you want?
Probably in the future need to gear them for because they're most likely not going to be strong enough. But as of right now, we don't need to gear them.
Okay. And so go back up a slide. Okay. All right. So I've never seen this picture before, but that's awfully, I think it's kind of cool. What kind of disadvantage do you get from having a dome, a 360-degree power generator like this?
It'd be big and bulky, so it'd be maybe more susceptible to damage as well. And it'd also probably be inefficient because there's a lot more materials and money going into this than there would be for just like one solar panel.
Yeah. Yeah. I think it's a nifty idea, but if we, only, 10% of those solar panels are actually generating very much power and the others are all generating very little. So although it's a cool look, I don't know that it's as effective as what they would like for the cost. But I think it's cool that you found that picture. I've never seen one like that. So
Glenn, I was about to say a similar thing about what that you just brought up, but the one thought I had about this is, could you adapt this so that wherever the sunlight came in here, it reflected the sun to a solar panel?
You might be able to.
Either reflected or refracted, something along those lines. I mean, it's Glenn brought up brought up a good point there. That having all it being solar panels, but what if you had the inside a spot where things went to? I think that's something you may want to look into.
That's an interesting thought.
Yeah, where all the no matter should be a dome that refracts all the light into a center point.
Either refracts or reflects something. I don't know if you could do something like that, but I just thought I'd throw it out there.
Huh. That is a different thought, Gene. I had not considered that either.
There's also the possibility, if you have these panels going all the way around this 360 degrees, obviously a number of those panels are not in direct line and are not functioning at that time.
Yeah.
But you talk about if this thing could rotate on a single axis 360 degrees, then you really only need to make a portion of this and then have it rotate so that those panels are always directly in line. You're with a flat panel, you've got to have movement on multiple axes. With something like this, you might be able to do that with just one axis. This thing would just have to be able to spin. Right now, it would come down to efficiency. Is that really going to work? But it's a possibility. Look into it.
Yeah, we could have like either one like wall segment wouldn't work, but like fold out like extendable solar panels. They could extend to like a long vertical thing, and then they could spin on one axis.
Yeah. You know, that's a neat thought there, Dave. I hadn't thought of that either.
Or you
Yeah,
could have something like
I
an
don't know how
umbrella.
efficient it's going to be, because but
Well,
Yeah,
we're
it's
gonna,
just a
we're,
it's
different
worth
path.
looking into, guys. Right?
we're definitely gonna look into that because that's a very interesting idea. And
Yeah, I mean, because again, I just don't see this as efficient. You're putting up a lot of panels that are basically not going to be generating any power at any given time, right?
Yes.
But if this thing can rotate, maybe you eliminate that. It's a possibility.
Yeah, I love that idea. And I was thinking maybe just even like an umbrella. And the solar panels are on the top and you rotate the umbrella. I don't know. It's like you gotta research that. That's why we hire you to look up these things and see just even how a picture can lead to different ideas. Did you have any questions for us?
Not that I have.
Nope.
Nope. All right. Well, there's another team at Council Rock that's going to present, and that's the Collapsible Mirror team too. Are they there?
Hey guys, one more question for you guys.
Okay.
So you were talking, you're going to use Arduino. Are you going to be doing this programming in Python, or what are you guys thinking?
Right now we're doing it in Sharp, I think, or C++.
C Sharp, C++. Okay, and it's just a curiosity. So I'm okay with however you want to program it, but yeah. Okay, thank you, gentlemen.
Yeah, thank you very much. And we look forward to seeing your 3D printing too. So is the other team there in the Collapsible Mirror at Council Rock?
They are over here, so.
Oh, awesome. Thanks. I'm trying to keep us on schedule.
Bye. Thank you.
Thank you so much. Hi.
Hello. Hello. How are you?
Good. How are you guys doing?
Good.
Hi. Was that Fred?
Yeah, I don't know what this is.
Yeah, you run your cursor at the bottom and you can share your screen. But you can introduce yourselves.
I'm Owen. I'm Marty. I'm Jake. I'm Ryan.
Hi.
All squeeze in. Yeah, please.
So there's 4 people on the team, is that right?
Yep.
Yep.
Excellent.
Just get another slide set, show on the board right now. Appreciate it.
The other team had their slideshow working real well. If there's
We found, we just hit the button to drive. We got it up.
You're on the
now.
wrong thing.
Yeah, we're good.
Good. Yep, it's coming.
That's good.
Yeah, it's good.
So we are building a retractive mirror for a lunar rover with collapsible mirror.
Alrighty, so our main ideas were based off of the James Webb mirror. And we basically just wanted to design some sort of mirror that would collapse to a small enough size to go on top of some sort of extending. So we have this extending pole that we would like to put a mirror on top of. Telescope-like base. And this was our first prototype of our mirror. It's an origami-like mirror that would extend. Pretty cool. We did realize that the refractability of it is not great, so we have another prototype that we developed. Those were our main ideas on the synopsis of the thing, and this is our prototype number 2 for our mirror. It's really hard to see, but basically we would put some sort of mylar sheet on top of it in a bigger scale, of course, and have a string that we could pull through to make it fit that conical shape and have that central point that it could point light off out of.
Interesting.
Yeah, that's a unique idea.
And these are some materials. So a spring would be hopefully a way we could extend one of our designs, which is this. Extend this instead of just manually extending it. And then we also use 3D printing filament and Mylar.
So for the actual mirror, we chose Mylar because it's not only cost effective, so it doesn't cost a lot of money, but it's also very flexible and can refract light from the sun. It is very flexible, so it'd be easy to maybe like and then retract and close back up.
For the retraction mechanism, like Owen showed you, our model here that we've made so far, it retracts through these 3 pieces. Each one fits inside of each other. And we're going to use the spring that we mentioned to hopefully find a way to make it automatically retract and make it easier to go back in on itself.
The research we started, we based a lot of it off of Glenn, the PDF you gave us. We really do appreciate that. That helped a lot. The James Webb was pictured in that, and so was the space blanket that we thought of Mylar. And as we went deeper into the Mylar research, we saw that it fit within the temperature standards and it was flexible and it reflected a lot of the light, which is why we think that's going to be the best option for us. Also started to reach out to Mylar companies. I don't really know how to pronounce that, but neither of them have gotten back to us. So I'm going to reach out to them again if you guys think that's the best option for us. And then we also spoke with our physics section of our science department, and they gave us more of a background and understanding along with your PDF of focusing light with parabolic mirrors.
Some more progress, obviously, that I've been mentioning throughout the slideshow. This is 3D design that extends in 3 times the size of its base, which is very convenient to extend to the height that we hopefully can put on top of the rover. And we eventually want to put a hinge system of the mirror on top of this. We have not got to create that yet, but we plan on adding a scaled up version of our prototype 2 for our mirror, hinge onto the top of our base. I believe that's a basis of it.
Dave, you're a lot more into the optics there. Would you like to start off?
Well, first of all, I'm really intrigued by your collapsibility. Is somebody there versed in like origami?
I saw that.
I'm serious. That's, you know, I can tell you that NASA had a lot of people studying origami when they were developing the James Webb, right? Mm-hmm. So that's really an interesting thing. Now, you're talking about Mylar. Will the whole thing be Mylar? You know, is it going to have a frame that just expands out and then comes to a certain size?
So definitely the Mylar would be only in the center of some sort of perimeter, because I figured that if you pull down a Mylar sheet, it's not going to pull down to a perfect like cone like shape to refract light. So hopefully we could add some sort of like concentric like perimeter circles on the base of like the Mylar to pull it down and not have like those creases and have it like perfectly reflect the light.
Yeah,
All right.
Mylar,
Go ahead.
Mylar would really only be the like the actual mirror portion. Everything else would be more strong and make the Mylar into the angle of the parabolic mirror that we want.
Yeah. So a couple of things to think about. If there's not much backing there, this is going to be pretty thin. One of the things that you're going to have to address is over time, there's going to be dust building up on this that's going to have to be cleared off. First of all, how robust is that Mylar in terms of, abrasion, et cetera? And then what mechanism can be used to clean that stuff off, right? Be thinking about those kinds of things. 90% reflectivity is pretty significant. So you're definitely on to something there. I like that.
Thank you.
Well, that's something you could talk to the Mylar companies who you're contacting. See if maybe they even have some kind of film they can put on the Mylar that could, instead of attracting dust, keep it away. I'm thinking of water, hydrophilic and hydrophobic, but maybe there's something for dust also that they could put on that Mylar.
Right. Right.
The one question I had to do with the conical shape, and you already made the comment here that you don't know how that you don't think Mylar is going to easily shape into that the parabolic shape you need or the conical shape. What are your thoughts about getting it to that shape while it's out there?
Yeah, so with this design, I'm hoping to put some sort of like base underneath of it. That's a bunch of like concentric rings behind it. So then when you pull through this, it keeps its conical shape instead of like in some sort of way like folding. We wanted to make sure it goes in those circles.
So you're talking about pulling it back in multiple areas?
Yeah, so I figured if you pull it down to only the middle, it would become not like the ideal shape. So if we had some sort of way to have multiple strings connected to different type of bases, like circles underneath of it, then my top of the head response to that is that's starting to get a little bit complicated. You may want to build that soon and test that out so that in case it doesn't work, you can switch to something else. But getting that shape is going to be the most important part of doing this. So, but I like all the work you've done already. You've done a great job. So.
Mm-hmm. So I really like you demonstrated in the beginning how you pull that string and it makes the shape of whatever frame you have on it. The Mylar does. The question is, how do you keep that shape? Is that the problem?
Yeah, so we had an older design that I couldn't really get developed, but the string would eventually go through the base, hopefully, and have sort of locking mechanism. Like there was this different project that we looked at in our classroom that had a locking design with like a metal rod where it locked and it pushed it back.
It's kind of like a parachute. You know, when you have a parachute, it actually has little places for the string all around it, and that holds it open. So do you have any questions for us?
Yes, we do. So what would you suggest for a mechanism to extend the mirror out? We were thinking either spring or hydraulics, but we didn't know how either would work with different gravity.
Yeah,
things like that.
We didn't know how gravity would factor into extending this with like springs and hydraulics. Do you have any knowledge about like how gravity would affect it? That's what we were.
Well, I think you've got some good options with springs. and exactly how to manipulate them, I'm not sure. Hydraulics is probably not something that we would want to use in space, just because of the temperature ranges that we're dealing with. You know, you go from really hot to really cold, which means your fluids would freeze up or get real sludgy like. But I think if you had like some kind of a spring action for the deployment, I think that would be pretty good. And actually, I had a question for you. In your talk, you use the word retraction, but I'm not sure. I'm not sure how you're using that. It seems like, I mean, here we're trying to deploy a mirror as opposed to retract the mirror.
So do you mean like you say you only want it to be extended after you extend it, like you want it to be permanently extended?
Yeah, so it's collapsed for when we launch it, but once we get it to the moon, we expect it to just be deployed the whole time. Is that the way you guys are thinking about it, or did I misunderstand?
It would stay permanently extended. That's why we use like the friction of these pipes to make sure it stayed that way.
Okay.
Definitely, we would have to factor in the different weights of the actual materials to figure out like how much friction, or if we need to add that spring to keep it that way.
Right.
Yeah, I also think we were thinking about building it all to the point where we could retract it to that one point that this would be at, and then once we get there, we would use those springs to then expand it out.
Oh, okay, that's fine. Did you have some other questions?
I have a question about the if you have any suggestions, because we don't have Mylar at the moment, to figure out the fold into this shape. Do you have any type of material that could be used as a substitute that we could experiment with Mylar?
Well, so I picked up one of these Mylar blankets, and you can order like 5 of these for $10 or something like that. And so when I pull this one out, it's funny. I used to be able to get these just going over to the sporting goods store in the camping section, but now they have ones that are a lot thicker, and I didn't like them as much. But you might check that out anyways. But if you go online and just say emergency blanket, you can get these things. And these are, I don't know, they're about 6 feet wide. Now, one thing to be aware of, if you hold this up to the light, you're not getting 90% reflection. You're probably getting more like about maybe about 50% reflection. But it's definitely something worth starting with, because as soon as you pull it tight, you lose. Let me pull it out. As soon as you pull it tight, you can get rid of almost every little crinkle in there, and so it does the kind of thing that you're looking for. So I think you can get I always like it when students are contacting the company that produces the stuff. But I think that you can get real cheap versions of this without too much trouble at all.
Sometimes it's even sold as a NASA blanket in the NASA's shops. Go online, look at it.
I
Any
gotta
other
figure out how to get
question?
it back in the box.
Yeah, I think we're good.
Yeah, I think we're good. Yeah.
All right, nice presentation. I like your ideas, and thank you for all your work on that. That's pretty cool.
Thank you.
Thank you. Thank you.
Okay, have a good afternoon.
You too.
Thank you too.
All right, so now we're not too far away. We're in Glenelg, Maryland. Let's see. Oh, yes, I see them.
Hi, I can share my presentation with you right now.
Yeah, that's great. Thank you.
So me and my partner Alex are in different locations right now.
Yeah.
But as you can see, he's just calling in from his home computer.
Yeah, I see that. That's okay. That's fine.
All right. Should we begin?
Yep.
Yes.
Okay. All right. I'm Grady Cronkite.
And I'm Alex Bertillis.
And we are the Glenelg Collapsible Mirrors team. Okay, so our project is basically that NASA wants to build a rover that's able to mix lunar regolith and polyethylene plastic together to form regolith bricks. These bricks melt at about 132 degrees Celsius, and it'll need a heat source in order to melt them.
Yeah, so while that rover's roving around, we want that mirror shape to redirect heat to the auger. And that's only for heating that auger, not the rest of the rover.
So during our research, we looked at past and present solutions. And while looking at old patents, we found that they all tend to fit into 3 different categories: dish, trough, and Scheffler mirrors. Dish and trough mirrors are both the type of focus balance reflector, meaning that they're very maneuverable and the focal point is outside of their curve, and they also have a centered weight. Whereas Scheffler mirrors are usually a smaller mirror and a larger array of mirrors that all reflect to one focal point.
Yeah, so when we researched all those different designs, we found our 3 bullet points of the things that these designs lack the most of, and that's maneuverability, because most of these designs are very stationary in big collection areas. Collapsibility, they're not going anywhere, they're just staying open there. And shielding from dust and debris, because that stuff is a lot more prevalent on the lunar surface.
Yeah,
so these are the 3 biggest things we need to address in our design.
And here are a few of our annotated sketches, just like initial brainstorming, such as the reflective surface umbrella, which is kind of an upside down umbrella shape, dish mirror type thing that reflects all the light up to a focal point. And then we also have the U-wing, which is our first idea that had to do with collapsing. It's a trough mirror with straight edges.
Yep, and those are both focus balance reflectors there. And then we have 2 more. We have a collapsing dish that sort of rotates out, collapses out in a flowery spiral sort of fashion. And then we have what we call our folding trough, which is a pretty simple just trough that just folds in half.
So we also have some design specifications that we need to make sure our solution meets. The first is that the mirror must be able to operate for 14 days straight, or 336 hours straight, because that is the amount of time that the sun is out on a lunar day.
Yeah, and our model that we make is going to fit within a 24-inch cube, but the actual model that we decide to scale up, we can make it as large as it needs to be to meet those energy production levels.
Yeah, and when we're designing and testing our scale model, we need to make sure we're being safe, because we're working with temperatures of at least 132 degrees Celsius, so we want to make sure no one gets burned.
So during transport, the meter has to deploy to half or collapse to half its volume. But once it's up there, it just stays deployed, doesn't have to recollapse.
Yeah, and when we're designing our mirror, we need to make sure we're using lightweight and durable materials. It needs to be lightweight because it costs about $1.2 million to send only 1 pound of material up to the moon, which is very expensive. So we want to keep the weight down. And we also want to use durable materials because once we have it up there, we don't want it to have it break and then maybe have to replace it.
Yeah, so based on all those specifications, we came up with a decision matrix here. We rated each of our specifications 1 to 2, and then rated everything else on a 1 through 5 scale.
Yeah, so as you can see, we have 8 different designs. Of those 8 designs, we found the top 3 were the reflective surface umbrella, the U-wing, and the folding trough, which I believe you saw all of those earlier in our annotated sketches. And the best one we decided on was the folding trough. But a little bit more about the specifications themselves. We weighted them on a scale of 1 to 2, 1 being just average and 2 being the most important. And we decided that the ones that are most important were collapsibility and maneuverability, because we need to be able to transport the mirror easily, and the mirror needs to be able to follow the sun once it's on the moon.
Yeah, and we also gave safety, longevity, heat generation, and lightweight a 1.5 weighting, just because those are very important factors that we need to consider, but maybe not as important as that collapsibility and maneuver.
Yeah. And so more on our best solution, the folding trough. So the folding trough is basically it's a parabolic mirror design. And it's also a trough mirror. So as you can see, we have a few components. The first component is the reflective surface, which is a parabolic shape and reflects light up to component 3, which can either be an auger extruder, that can be where that is, or it could be a pipe containing fluid that can absorb the heat that's being reflected to it and transport it to wherever it needs to be. And we also have component 2, which is a joint that the mirror can fold and collapse along.
Yeah, so based on our, oh, you skipped past the mock-up. There we go.
Sorry.
So our first mock-up on the left is a bigger one, just to give us that general sense of that shape and what we're working with, how it's going to collapse. And then the mock-up on the right is a more scale model, and we made the joints function a little better, gave us a much better idea of what we need to focus on. And so the biggest takeaways from the mock-ups were what are going to be the problems of this mirror? Maneuverability and collapsibility are definitely going to be the things we need to focus on the most.
So from our mock-ups, we took those designs, tweaked them a little bit, and brought them into our CAD model. So our CAD model, similar to the mock-ups and the sketch before, has 3 main components. The reflective surface, it's also a removable reflective surface. The idea is right here. So the idea is that if that surface breaks, you remove a few bolts, and then you can take it out and replace it with a new one. The reflective surface itself is a curved piece of aluminum that is coated with a mylar film to make it more reflective.
Mm-hmm. Yeah, and the rest of that design should be mostly made of aluminum there too as well.
Yeah, and then as you can see at point 2, that is the joint that it's going to be able to collapse along and should collapse it to less than half of its volume when it's deployed. And we also have a GIF of it opening and then the parts exploding out. And then we also have a rendered model on the right.
Yeah, and the biggest thing is that, oh, hold on.
Oh, yes, sorry.
You can see those 2 sheets kind of fold out there, just a visual representation of that removable surface there.
So then when we were making our CAD model, we wanted to make sure it was as mathematically accurate as possible. So we used Desmos to model a parabolic shape that's about 14 inches long and has the focal point of almost 4.1 inches above the vertex.
Yeah, so based on the CAD and some other calculations, we found the total area using length times the arc width of our parabola there. Considered the solar constant on the moon and the reflectivity of mylar, and came up with a total number of 237 watts of output for our scale model. Not the
for your scale. Wow.
Yeah, our real model can be scaled up to however many watts is required. And then we also met with Mr. Robert Tate. Yes, a NASA engineer who has a lot of familiarity with mirrors. And he gave us a few ideas for our further research, such as for maneuverability. He wanted us to look at a heliostat, which is pictured on the left. We could possibly use that for our design or some element of it. And then
this Dobsonian telescope design as well, which would be a little more maneuverable than that sort of trough design that we had. So these are 2 ideas that we can consider and sort of do more research of and focus on in the future.
Yeah. And here are references for our research and our presentation.
Yeah. So we have a few questions ourselves, but we'll let you guys go ahead with your questions first.
Dave, you want to start?
So you guys are thinking about mylar as your reflective surface?
That is correct.
Okay, and your panels look like they're going to be solid. So is that just like a mylar coating, or what?
Yeah. So we're going to do what we're thinking is we can shape an aluminum sheet into that parabolic shape and then coat it in a mylar film.
Okay. All right. Very good. Yeah, I like what you guys have done. You've obviously got all the math worked out there. That looks really sweet. I'm impressed with that.
Thank you.
Yeah.
Thank you.
Yeah, so we have a few questions. So once the auger gets up to heat, it's going to require a lot less energy focusing on it to maintain that heat. So what we were thinking is we could maybe redirect the mirror once it gets to that point to a sort of heat battery that might be able to store heat and then keep that Rover production going, maybe a little past that daylight hours.
Well,
that design.
I think, so why do you think that once it gets up to temperature that it doesn't have as much work to do?
Right. Well, it's
Well,
trying
we
to get
don't-
that. Oh, go ahead, Grady.
So once it gets under temperature or even like far past the temperature, we don't want it to say overheat. So depending on how much heat is being reflected by the mirrors, it might be worthwhile to redirect it somewhere else. And if we do that, it might also be worthwhile to have some kind of heat battery. So then maybe after the sun goes down, we could keep going and produce more bricks.
Okay. Well, and part of what I'm asking is that, so you're going to be feeding cold material into it all the time. And so you might be getting it up to a certain temperature, but you're also trying to maintain that temperature as you feed in more and more material. Does that make sense?
Right.
Yeah.
So
makes sense.
it's not just that it's at temperature, you're having to maintain the temperature because of the materials you're putting into it. Does that make sense?
Okay, so when that auger's going, that got it. Yeah.
And that and material we're putting in there is going to be pretty cold material.
Right.
So that's a big thing. I have to say that I really like the simplicity of of the mirror folding in on itself over that pipe, that central pipe. So very nicely done.
Thank you.
And we had one more question.
Yeah, go ahead.
So when that mirror is expanding, once it goes up to the moon, does it have to be automatic or can it be hand driven?
There won't be hands on it, right? Meaning that we expect that the astronauts, this will land and be deployed, so it needs to be able to deploy itself. Does that make sense?
Okay.
Right.
So
because what we were thinking is we would consider maybe a hand crank because it'd be less electronics, less power.
Oh, well,
yeah.
And you can demonstrate with a hand crank. It's easy enough for us to imagine a motor instead of me hand cranking. That's not a problem at all. So you don't have to demonstrate with a motor. Having a hand crank on there is just fine. I also like the simplicity. I like what you're thinking there. Because you're dealing with Mylar, you can probably lighten up some of your mechanism there. You may not need the big thick ribs that you've got because the Mylar is so lightweight.
Yeah, we were thinking about either cutting portions of it out, making it sort of a truss design, or just thinning it out entirely.
Sure, and you can even put lightning holes into it, just and lighten it up if you still feel like you need all of that rigidity, which actually has some value, just because you can imagine this thing may be bouncing around, and so having some rigidity to it might be important as well, just so you don't have fluttering kind of things. No, I like the way you're doing that. I could see that rather than just one kind of one clamshell opening up, I could imagine that you could have multiple hinges on there if you wanted. Is there the question is more just about how much space can we save, as well as keeping the weight down. Excellent job.
Can you go back to the CAD for a second?
Yeah, totally. The GIF or the
stationary one.
Okay.
Yeah. So are you suggesting maybe another hinge, maybe halfway along that surface?
Potentially, and it's just something to think about. It's not a requirement. It could be done in that way, and then you would, but it would be a staged deployment. Does that make sense?
Right. You have the
Because
first
you'd
bit
want
pulled
it to
out, and
open
then
all
it
the
would-
way out first, and then the secondary one. Just thoughts, not something you have to do. I like your CAD that you've got. It's very descriptive. And I like that you've already calculated out the sizing for that you're aiming for. I think that's really smart. I'm really glad you talked to Mr. Tate. I think that he's done some great things with us before, and the fact that
Yeah,
you
he's
guys
been
are
a
talking
really
with
great
him,
resource for us.
excellent. I'm glad. Excellent job, team. Keep it up.
Awesome.
Thank you.
Thank you.
And a really nice presentation. We really appreciate. Everything was like professional. Look at all those references. Oh my
Thank you,
goodness.
Dr. Gold.
Thank you so much.
Thank you.
All right. Thank you so much. All right. So now we're back to Bozeman. We're going all over the country here. We're in Bozeman, Montana.
Switch it to the.
Hello?
Yep, we hear you.
Okay, we hear you.
Switch it to the
Bozeman High School.
So one is faced.
And they are doing the collapsible mirror also.
Yes.
So
Excellent.
did you listen to the last two presentations?
We heard like the end of the two presentations ago. Yeah, we saw
Okay.
the last one.
Okay, good.
One moment. We're having some technical difficulty.
We'll stand by.
All right.
Just had it. I don't know. We clicked and it's not there anymore.
Such a bummer.
Your teacher is an expert at this, I like you to know.
Trying to. Right now, none of my scenes are showing up though.
Let's see, we see
Oh, it's a software side. It's on my end.
Oh,
here it is. For some reason, it got shifted over. So it's this thing. So that's what you need to. This is how you're going to switch between scenes. So this would be like, oop, where did it go? Does that work now?
we see the mirror shape slide.
Hopefully they're not reading it.
Yeah, we're trying to be able to switch
Spoilers.
between cameras and it keeps going
It's
away.
like on which side?
Okay, so there's
Now
that.
we see you.
What do we click? You got this.
I can do
Okay,
it quick.
so it's this right here.
Okay.
So like if you wanted to switch to the dot cam, that's number 2.
Okay.
And then your PowerPoint number 3. So it should, nope, still not working. So that's where you would click instead.
Okay.
So
I
under
can
scenes-
just do it on the
Cool.
mouse and we should be good. Hello.
Awesome.
Hi.
Good afternoon. Oh, wait, it's
We're
morning.
ready. Here, let me get us on the first slide real quick. So we also did the collapsible mirror.
No, all right. My name's Finn Berg.
I'm Ian McLean.
And Bozeman High School, working on the collapsible mirror project for the Rover.
So we
Yeah,
chose
yeah,
this
you gotta
project.
switch to
Oh yeah. The webcam.
3. Oh my god.
Okay. So
Right, full screen.
we chose this oh god.
Okay.
Okay, so we chose the collapsible mirror project because we like the idea of turning like the plastic waste that the astronauts use and like putting it to use and using it for like building blocks for like, the moon. And so we started off with our two main designs. We had a parabolic like
a square shaped mirror
Mhm.
and a disc shaped circle mirror.
Right here.
And our two designs, we eventually went with a square mirror because it would be easier to mix the materials together as it goes through the pipe and gets heated gradually, was our thought, rather than the disc mirror, which would just concentrate all the heat to one point.
Yeah, and also when it's like a square shape, it's a lot easier to figure out how it folds, which just makes it simpler, and simpler is always better.
Yes.
So we just decided to go with the parabolic, like squared taco shaped one.
Yes.
So so it would go to like this. Can you see my mouse?
Yes.
Okay, yeah. So it'd go to this point right here, which is like a
Oh,
tube, which like has an auger inside of it. We would imagine. We talked to like the auger group a little bit, and they imagined like there'd be this tube, which like would have like a, what's the word, auger? Just
Yeah.
auger.
Mhm.
With like the regoth and the plastic going through it. and as it goes through, it will like melt, and then it will go to the extruder.
Switch to this one.
Okay, yeah, I got you.
Yeah. There's 2, I think.
And it's
And-
regolith, regolith.
Regolith? Oh,
Yeah.
that's how it's
Yeah.
pronounced? Okay, right. Thank you.
And we don't have all our drawings from our notebook on our presentation yet, but this was part of our design that we figured out is that the angle of reflection from the mirror and stuff, we calculated the mirror to like be the right size so that it's as small as possible, so that like if the shape, like I don't know if you can see this, but if the shape continued going up here, it would be like wasted space, like because there'd be more material to do less work. And so we calculated this point right here to be our equation for our shape and design of our mirror.
So how high off of the mirror are you expecting the pipe to be?
It's gonna be level with the top of the mirror to like maximize or to be as small as possible. Is that
so? Like in this image here, let me go back to the yeah. So right here, you can see like in this image, this is just a random image we found. So it like goes a little bit above this point, but ours is going to be flush with this line right here, just to make it as small as possible, obviously.
Yeah,
that's fine.
Yeah.
Okay. And so have you figured out the size of mirror that you're thinking about, or how's that going?
Well, for our prototype, we're gonna make it probably like a foot long, because well, we're thinking about 3D printing a lot of our parts, and that's like the size that would work best for the 3D printer. But for the actual one on the moon, there's
24 inches.
I mean, it's hard to say exactly how big it would be because it depends on how much plastic you're melting at a time and stuff like that. But I don't, we did some math to figure out some things, but we don't have a strong estimate because like it really just depends on the other variables that are decided.
And we're thinking it would be roughly like 24 inches maybe, or like 24 to 30-ish. And since we're 3D printing, we can pretty much just do whatever size we want and then just like super glue them together. Also, another point, we were thinking for the reflective surface. So we have like a little bit of a prototype here.
Yeah, let's hear a prototype.
It's just a
here,
piece of the.
We'll go to the slide real quick.
Ian, go to the on-shape thing.
Yeah, I got you. One sec. So this is what we've printed, and then this is our like full design. So we'll just go here real quick.
Okay. Actually, go back.
Go back.
So this was like a piece of our design, or that's our full design, is what we're thinking. And I guess I'll explain it first.
Okay.
So our idea for the movement is that we have like a gear around it with a motor connected so that it spins like
around. So this spins around.
pipe.
Yeah. So it spins around this axis.
Yeah. So that no matter which way it's facing, it'll still concentrate the light towards the pipe. And then the folding design, you can see it has a lot of parts, and it's connected by small hinges that we've made. And
yeah, I'll go to the webcam real quick.
And then we made a small piece or a part of it to test like a lot of the moving pieces. And so this is like the end piece you can see on the thing. And we got pieces, we made hinges to test the moving ability and the design of our hinges, so it would compact and pretty well. And then this is kind of hard to show, but we have our mirror folding up like this, and
then obviously it just like the mirror would extend the full length. We just didn't want to print all that just because it's kind of a waste of plastic.
Yeah.
But yeah, exactly. We just wanted to like test the idea and see some kinks, which we still have like a little bit of kinks to work out. But so this would extend all the way out, and then on the other side we would have, so like there's this, but on the other side, and that's where our gear is going to be, which you can see on here. that's where this gear is going to be. And what was the gear ratio?
Yeah, and we're thinking about adding a gear so that the movement or the motor controlling it has more control, and it's more stable and sturdy rather than just having just a motor holding up the whole mirror.
Yeah, because if we add a gear, then like there would be more weight that would be like evenly distributed.
Okay, and I'm impressed with how small you've got it folded up, but I'm not quite sure how does it get deployed? How are you guys going to make this move out?
We were hearing this in the last presentation, and we didn't really realize that it had to like self-deploy, you know. But we kind of like we're just starting to brainstorm some ideas about like just like within the past few minutes. And here, let me go over here.
No, that's okay. Keep going.
Yeah. So from this side angle, we could have like some like pistons or something like here, and they would like extend out, right? And then like it would go together. But the problem was when it extends out and goes back, this hinge right here, like there's nothing like supporting it. So we need to find a way, like either that be getting rid of this hinge, which making it less smaller, but it would make it self-deploy. So it would extend out like so, and then like come back together. But the problem is we just need to like figure out a way for it to stay like this.
How do you attach it to the other side?
So we have this here. We 3D printed another part. So we have this like little piece right there.
Sure.
Right? And then it just clicks in like so. And then on the other side, around the mirror, we have that same sort of design where it just clicks in like that. But the problem is it's not autonomous.
So that, there's a toy that's made of wooden blocks, little like 2-inch by 1.5-inch wooden blocks, and there's a ribbon, and then you let the toy fall down, and then it also collapses. Have you guys ever seen that toy?
No, I don't.
It's called a Jacob's ladder. Is that right?
Yeah, that's what I'm talking about.
Yep.
That might look up Jacob's ladder. That actually is segmented into little. Your design reminded me of that, and that actually collapses and opens itself, and it's just by a ribbon.
So
Hey guys, what material are you thinking about for your reflective surface?
So for the reflective surface, we were thinking it would be like a 3D printed just because it's very light. And then we'd have, since obviously 3D printed like materials like super rough. And if we were to connect like Mylar to the top of it, it would be like super like ripply.
So you're thinking Mylar is your choice?
Yeah, like the same last groups. We're thinking about like having a base material and then having like a layer of Mylar over it.
Yeah.
So here's a thought. Mylar is fine, right? And certainly there are some advantages regarding weight and that type of thing. Solar sails right now are an aluminized Mylar. That's kind of one of the sources. And the reason, my point is, look at other materials, an aluminum oxide, a silicon oxide. There are a number of other things that have a much higher reflectivity than Mylar, right? And it just, let's not just stick with that one idea there. I think that this is worthy of doing some research. The reality is we're going to invest a lot of money in this. So we can't just make weight the only consideration, right? We got to make sure that we're getting the highest degree of efficiency out of the system. And there are alternatives to Mylar, which are better. So look at that.
Yeah, for the actual design, like we'll definitely make some changes, but at least for our prototype, we were thinking about using Mylar because it's like it's just
I get that, and that's for prototypes that's fine. Obviously you're kind of constrained on accessibility and cost, etc.
That's kind of hard to find.
But do the research, and do a good comparative analysis of different different materials.
All right.
Mhm.
Okay.
Okay, yeah.
Yeah, and so for the critical design review, have suggestions what NASA should use, but you use Mylar.
Yeah.
Does that make
The one-
sense?
Yeah, and the one suggestion I had for if you go to your D shape that you have that when it unfolds and you create that curve, right?
Right.
If you once it's attached, if you were to pull it in along that line, it'll stress the other, it'll force the outside curve into a permanent position.
Yeah.
Even with the hinges there. So pull it out and then somehow have something that brings it in and kind of forces that outward flex to stay permanent.
It's hard to keep like, I mean, we have like 1, 2, 3, 4, 5. We have like, here, let me get the webcam on real quick. We have so many hinges. It's really hard to get like a sturdy design, but I just really, I like the idea of being able to keep it so compact and small.
Yeah.
It's just really hard trying to find like a way to like make that sturdy, you know, and make it like autonomous as well.
Yeah.
Well, you just learned you had to do that, so.
Yeah, so
right. That's why you build your prototypes, is to go through those failures.
So one thing I was looking at with your design was with the auger pipe there, I'm thinking if you rotate your auger pipe so that then so that one side is drawn towards the center and the other side is also drawn towards the center. Does that make sense?
No, I'm not really.
I'm thinking you might be able to roll it up around your auger pipe.
I think I know what you're saying.
Yeah.
So like when it
And
folds around the pipe.
Yeah, and it might be that you're. Oh, okay. Okay. Snap bracelet. Think of a snap bracelet.
Okay.
So your two straight pieces there. What if those two were snap bracelets?
Oh,
and
like,
each side is attached to your piece, to your mirror.
Yeah.
And if you simply rotate your center auger pipe, would that?
Oh, yeah, no, I see what you're saying. Yeah.
I'm not sure if I'm seeing the whole thing, but I'm trying to use your setup there. You might be able to use just your pipe itself as being part of the mechanism that pushes that pushes it out. Does that make sense?
Yeah, no, I know what you're saying.
Well, that was like one of our ideas. This idea was kind of like it would just go around the actual pipe that they were using on the thing, but like, or I guess it makes sense what you're saying.
Yeah.
Mm-hmm.
That logically to make the whole thing spin. That
Okay, wait a minute. And I'm trying to kind of complete my idea here a little bit.
Yeah.
So each leg going out from the pipe would be a separate snap bracelet. And as you
like
rotate it,
ones.
yeah, so it would be 4 separate ones. And then as you roll it inward, they would the sides would come together.
Okay. We might have to switch up some of our like hinge design for that, but I see what you're saying.
Maybe. And remember, don't pretend like I got the answers, because I don't, right? I'm just throwing ideas
we're
out
open to
for you.
ideas. Right, here's our shape.
Yeah, this is our actual design, so you can move it.
Yeah. Yeah. And so what it would do is they would kind of just drape down. All it would be doing is making it come out to the full dimension. Yeah, I don't know. Just something to think on, guys.
Yeah, I kind of know what you're saying. There'd definitely be a lot of things to work out with that, but I totally see what you're saying.
Be solid.
Yeah.
It's just another aspect that it reminded him of slap bracelets.
Yeah,
And
we looked at the
the
Jacob one.
auger in the middle is the wrist.
Yeah, exactly.
Yeah.
Sorry, I dropped off there. Anyways,
No,
I like
that's
where you're
good.
going with this. You guys keep going, okay?
Yeah.
Okay, yeah, and then we only have a few more slides, but
We literally don't have any more slides.
Do you
we
have
just had this
any
prototyping, and then
questions?
this. Well, do you have any questions? Because yeah,
We kind of asked
think-
ours, but do you have questions?
well, I mean, if you could think of it, I don't know, like any off the dome ideas about how we could make this like.
We already got some ideas.
Yeah.
I mean, I think we're pretty good. I think our biggest problem is just making this like autonomous.
Yeah.
Yeah.
And we could mess around with that like folding idea where this like snaps like a snap bracelet.
Yep. Yeah, no, I like your design. I like how it collapses too. Good. All right, then. And you can always
Good
send
job,
me
Jim.
questions and keep me informed on
Yeah, for sure.
on your design. So thank you so much.
Yeah, thank
All right,
you.
Thank you. Yeah.
All right. So actually we have time to move into, we have two more. The lunar work table from Maine. And then we will move into PCTI because I just got the message PCTI doesn't have to leave until 2:50 today. So we should have time for both of these.
Unmuted? Yeah, we are.
So Wade, I think St. John Valley is going next, if that's all right. Do you have time, Marianne?
Yeah, I'm sorry, we're playing around over here.
Yeah.
Yeah, we should be okay if that would get us on to you by like 2:20.
Yeah, that's
Yeah.
more than enough
2:20.
time. Yeah, we
Okay.
should be on by 2:15. Okay.
Okay, good.
Yeah.
Yep, we're good with that then.
Thank you. All right, so St. John Valley Technology Center.
Hello, can you guys hear us?
Yes, we do.
Sorry, mic wasn't working for a second.
No, it's working.
Our crew has to leave at 2:18, so that works out really well for the other school too. So
Okay, that's great.
I got my two guys here. They are ready to go.
Awesome.
So yeah.
So this is the lunar work table with power.
Yep.
And
yeah, we can hear.
the problem we're trying to solve is to make a workbench with power and it's cost effective by making the weight as low as possible, and we need to make it compact so it can fit on the rocket ship to space. So this is our design. It is at the bottom there is like a dolly sort of, so they would be able to transfer stuff around easily on top of it. And also that's our table with power outlets on the top. And we go back one more.
Yeah, I click on it.
And then we got the light at the top, the power outlet strip, the tool holders, the cutting board, and the what's it called? Extension cord.
Yeah, extension cord.
So that's it for that one. And the top left one right there is where we got majority of the idea from for the dolly. And the second one is another picture of the top one.
But with legs folding in, so it won't hit any rocks or something when you're moving it.
Yeah. And then the bottom left one.
Just the same as top.
Yeah.
Just dolly. Or brainstorms ideas. Go first.
I said we plan on making a combination of all of the tables in research because they are good ideas and fit all the criteria that we need. All we need to do is add outlets and extension cords and a pegboard to put the tools the astronauts would need.
And my idea was the idea of the table that we are creating is a table that removable and easy to fold up nicely into a nice square or dolly that can help add power to dust. Yeah, sorry for my reading. Outlets connected to the table so you can plug things into so you can plug the items in and for power if you need it. Or you can also have the covering to keep it dust proof from like dust if you're sawing like rocks or something, and dust won't go in there. And we have like wheels so you can move it easy, like get heavy boxes on, and you can put the boxes on them easy. That's ideal.
So the criteria we need is aluminum table legs, hinges, wheels, plastic tabletop, extension cord outlet, and a pegboard. And the constraints that we have is it needs to be lightweight and what's it called? Small as possible, so it can fit on the spaceship
without having to like overprice or something. Yeah. Okay. Here's our pros and cons. We didn't get any cons yet, but we got a couple of pros for here. It can be like a good dolly to move heavy things around really easy without using without using like muscles or something, and that would like make them wear out and make it harder for you to do things, and make it have powers, dust proof outlets so dust won't go in them and damage any wirings, and then so you can plug things in so you can use power. You can use like a drill or something, and we also have like we're going to add like a light on the top so we can shine light that down if it's like dark. You can use the light to see if so what you're looking at. And here are like website drawings of our ideas for the tables.
Mine's the one on the right with the rubber wheels, and the yellow box on the right side of the table is the extension cord with the outlets on it. And then that's the tool holder in the middle right there. And that's where you can put all your tools. And at the top, there's an outlet strip, which you can just plug all of your tools into, and the light at the top so you can see what you're doing.
And the wheels there to make it a go dolly.
Yeah, and the legs right there are gonna be folding in. So the wheels would what's it called? You could move it with the wheels.
Dolly.
Yeah, but the legs have to move inward so you can move.
Foldable, yeah.
Yeah,
foldable. For my pictures I have right here is that this thing you can as it says right here, you can like put it down so it can become a box. So you have like the light here with some like outlets, so you can put it on the table like right here. Like you have an outlet to put them right here. And if you need it on the ground, you have outlets right here to put on the ground. I didn't want to add the dust proof covering because that's going to be a little time. And here's the extension cords. Right there, it's like the wheels on each side. You can't really see. And here's the legs with the like you can fold up. And here's a toolbox right here for wrenches and your screws right here, or what's that thing called? Tape measure. You can put your tape measure in here and stuff. And you can like take this out if you need it. You need some room to pull it. So yeah, that's our idea. We don't have any more slides.
Very good.
Yep.
Thank you. Well, you
Interesting
are,
concept.
yeah, you're the first ones who thought about making it as a dolly, and I think a dolly might be really useful up in space. Things don't weigh as much; they only weigh 1/6, but still, they could put a lot of things on a dolly and move it all at once. I don't know. We'll let the reviewers talk. Thank you.
Like 5 boxes without having one per box for your arms. Yeah,
the reason I like the dolly is because there's a way, and you didn't do it in either one of these table ideas here, but if you had the table go up and leave a major part of it down low, you keep the center of gravity of the table down low, and therefore you end up keeping it so it's not as tippable. When you raise everything up on the legs like you have here, the weight of the dolly now is up high, and the astronauts are going to be very klutzy and will bump into it and could fall over. So I like the idea of the dolly. I think that is but having the whole thing go up on the legs, I think you should re-look at that. And one last thing, the wheels, you're going to want to also look at, because wheels think of taking a wagon across Sandy Beach. That's what you're going to be doing here. So now I'll let Dave speak now.
Yeah, I'm a little concerned about, those wheels are probably going to get gunked up with material pretty fast. So can you go back to that image of your two side by side ideas? The one that had the wheels on it. So do I understand then that the image that was on the right, yeah, that one there.
Okay.
So those wheels are basically for the purpose of the dolly, right?
Yeah.
Okay. All right. I think Gene's comment, what you guys should do is just get some wagon wheels or something and try dragging that across, some really loose material and look at how that's going to interact with those tires, how it's going to interact with the axle that the tire is on, etc. That can be problematic, right?
Well, the class is working on scooter wheels, and they could just use the scooter wheel development that they're doing.
Yeah, be careful, because that's, the wheels that are for the scooter are going to be a lot larger and maybe heavier than what we might want here. Because I'm going to be taking this out and putting it back in and taking it out and putting it in, we want to make sure that we keep this as lightweight as possible. And so I like the idea of being able to hang up a couple of tools on the table, but try not to go to do too much of that, because now I'm carrying around a lot of tools along with the table itself.
Yeah.
But I think that there's some real value to your arrangement here. And just as another thought, I think you can see, originally I said 4 outlets, but I think that you can probably drop it down to 2 outlets. And the purpose there is just so that your table is acting as the in-between spot for something that's really high amperage. So for example, if I'm going to weld way over here, I can set up my table and plug in my welder to the table, and then the table has the extension cord that goes all the way back to the back to the Rover, so that I'm using the Rover batteries to do my welding. But probably just 2 outlets is all that's necessary, and that'll save you a little bit of design effort there as well.
I might have an idea for tools that I talk about. For like the tool, like right here, you can put there. I can actually make it like this. It can go like a little lower, and keep this one up so it can like fold nicely with the tools inside, and have like a little tray right here, like an empty tray, so you can put all the dust and make it fold outside.
I'm okay with that.
Okay.
Yeah, just try to keep it. We don't want to. Every time I lift up a table, I don't want to be carrying, another 20 pounds of tools or anything.
That's
So
what we for also. You can just grab
sure,
Yeah.
sure, understand.
So, yeah.
Now, I think that one thing I like is you've got the light up top as well, and I think that that's also valuable. Just as something that can be moved around and used to be able to give good lighting. So that's a good idea. And I'm sorry, on the right-hand side of so Everett's table on the right-hand side of the table, there's a yellow thing. What is that?
That's supposed to be like the extension cord. Like you can
Oh,
actually,
okay.
like roll it in, kind. You can actually take.
Oh, okay. So
That's what it
so
is.
the
Kinda like
yeah,
this.
the extension is directly underneath the table. Is that correct?
That's actually kind of on the side also.
Yeah, yeah.
That's on the
Okay.
side.
I'm with you.
Yeah.
All right. Good job.
All right.
So one thing you have to think about is what Jean always mentions, that we don't want the table to fall over. And so that's why he was talking about maybe even moving the, like a shelf maybe that could have the wheels towards the bottom so that the weight isn't all on the top. I don't know if you can design something like that, but he's worried about it being top heavy, and then when somebody hits it, it will fall over. And make sure in your designs you don't make sharp corners or edges either, because the astronauts will be bumping into it, and we don't want to hurt their spacesuits. Does that make sense?
Okay.
But
Good job, guys.
yeah, I really like the dolly aspect of it. That's the first.
If the wheels wouldn't work in space, could we like do skis or something? Like something, because you said it was like sand.
Yeah.
So
Yeah.
skis could like glide across it, the top of it, right? Sort of.
That's an interesting thought.
Yeah.
Because like you could
Um,
see it behind you.
Yeah. I mean, if you get, I don't want you to ruin a pair of skis, but it's, you know, if you took a pair of skis and pulled it across the sand, it would definitely be better than trying to, you know, trying to
Wheels.
drag something else. Yeah, wheels, there are places for a wheel and there's a place not for a wheel. I don't know which one is going to be better, but I see some of your thought process there. That's not bad.
Yeah, and they're in Maine, so they got snow. And so if you do take it out in the snow with some skis or even a snowboard, make videos. We want to see videos of your testing that.
Yeah, we will definitely record ourselves doing that.
Yeah, that'd be pretty cool. Do you have snow?
Yes, we do.
Yeah.
Oh.
Good. All right. Do you have any questions for us?
I don't really think so.
So up here.
Let me turn back on real quick. Oh, there we go.
Wait, how do you get into it?
Here. And click this right here.
So you said it needs to be lower to the ground, like the bottom left one there, how it's closer to the ground. Is that what you were looking for?
Huh.
So it's not movable, like you said, the weight distribution.
So we're talking about the once it's set up as a table, lower to the ground, but not the tabletop. Something like a shelf in there. I kind of like the legs that they spread out a little bit. Jean, you want to tell us what you always say about that?
About having it not top heavy, or
yeah.
I'm a klutz, and I think everybody on the moon is going to end up being a klutz. I really got this picture in my head. I watched an astronaut trying to pick up a shovel in their testing area when we were there a couple months ago, and that is stuck in my head about how hard it is for them to do even simple things. So having this table next to them that they're working on, I've worked on a bunch of tables, and I've knocked over a bunch of tables that are light. And so I really want that mass, the most massive part should be in the top, but it's a work table. So you want the top to be able to be hit with a hammer or whatever. And so there's a game to be played here and testing out how to make something so that it won't tip over while you're working on it. And I think your ideas here with the dolly and the skis, maybe a combination of the two, like a regular dolly has two wheels on one end and something on the other end, maybe to pull. I don't know. You got a cool idea that you could probably expand on. That's what I would suggest.
And you see your top picture here, the first table on the top. You see how the bar goes across the whole bottom? maybe what you could do once you set the table up is cover that bar with regolith to hold it in more. You know, instead of a bar, maybe even with a flat surface, maybe with a ski, and cover it so the sand on the regolith helps hold the table down. So the problem is we don't want the table to be knocked and turned over, if that makes sense.
Yep.
And the 4 legs, that would happen, but maybe I like the first design because it has a bar between it, and maybe that could be a ski, and you could cover it with sand or put a big rock on it. Use the stuff that's on the moon.
Okay. Good job, team. Thanks a lot.
Yep. Thank you so much. Wonderful. Thank you. Enjoy the snow.
And get a t-shirt like he's got, because that one's cool. Your teacher with the skull there, that's the one. Look behind you.
I like your t-shirt too. Awesome. Thank you. Bell's gonna ring. And we got the other team in New Jersey ready to go. And that's the last one for today, guys. Thank you so much.
Okay.
Okay. Oh, we lost Glenn somehow.
No, he's still on. He's just not on the picture.
I'm
He's
here.
there.
Don't do anything. What? Well, do you see us?
Yes, we see you and we hear you talking.
I know, but you have to talk. Tell them about yourselves first.
Yeah.
How are you guys doing today?
Awesome. How are you doing?
Doing good.
Thank you for
Also,
asking.
Of course, of course. Just for an introduction, my name is Isaiah,
My name's Stefan. My name is Franco.
and we decided to do the chair.
Awesome.
Share. Let's go to the slideshow. That's fine. Okay, so it's fine. Okay. Yeah, okay. Cool.
All right. So do you see that?
Yes, we see it. Perfect.
Cool. Can we skip the next slide? Now does an introductions, right?
So just to skim over the constraints, we just wanted to make sure that everything here, if anything has changed with you guys, if you guys wanted to add anything to it, just to kind of look over it real quick. We would need something obviously lightweight because it costs a lot to make something heavy to send it to the moon. And our setup is, we're planning on making it more efficient. So it's probably going to take up to 3 to 5 minutes maximum. And then we want something that is non or low flammable, sturdy, and for the conditions that are going to be in the lunar habitat. And then the height, we're gonna definitely make it like adjustable and multi-purpose because we know you guys are looking for it to be for a dining table as well as a working table. So last but not least, I feel like this is one of the more important aspects. We're gonna make it collapsible and easy to contain. So this is our like very rough prototype of the chair, as you can see. So we've just been grabbing stuff that we could find around the room, and honestly, it came out pretty all right for our prototype, but we will be making improvements. So with these initial sketches, we did play around with ideas a lot. So if you look at the one on the left, the problem would be is that it wasn't very sturdy, like it was a bit unbalanced, and we would have needed 2 levers to kind of recline it. Then if you look at the idea on the right, it seems all right, but when you actually started building it, the 2 pieces on the side that are going to be a part of the base, they kind of left you a lot of instability, and if somebody was to lean back, they would end up falling back. So that's why we kind of scrapped that idea.
Okay, so we just want to quickly go over the components. It kind of reflects like an office chair, so you'll be seeing a gas cylinder in our design. Obviously, it works on pneumatic principles. Air flows into a chamber, pushes up the piston. There you go, the seat is adjustable in height. Then you have our seat plate mechanism. That's where we'll insert our actual piston, and that'll connect to the top of the chair where the seat is. And then we'll have our hinges, more on that later, but they'll be able to rotate from 0 to 90 to hopefully 180 degrees. And then we have our base, which has 3 protruding legs. It's just for our prototype though. So these are the materials that we're planning on using. The conditions of space, we know that things could get hot maybe when they're sending the actual chair to the inflatable habitat. So we're hoping to get things with heat resistance and resistance to tearing. So as we can see here, carbon fiber, aluminum for the framing of the chair, those are adequate for, because they can withstand intense amount of heat, and they can also withstand the weight of the person sitting on the chair, which shouldn't be too heavy. And of course, we have our polyester fabric and our Kevlar fabric. Yet again, comfortability and tearing. So those are the main purposes of these materials. Just to quickly go over this, the chair, for it to be collapsible, we're going to have the backrest hold onto the actual seat. And then the gas cylinder on the actual prototype will, of course, like an office chair, go up and down. So it'll be HUD adjustable. We're looking at concepts of arms right now. Some will have a height retractability and some will rotate, so that when we actually fully collapse our chair, it'll be like nice and squared off. And then we also have rounded edges, obviously inflatable habitat. We don't want to puncture the actual habitat itself. And this is just a little visual demonstration for you guys. We have on the left here, we have our open and closed of the chair, just a side view. And on the right side, this is what we're hoping that it'll achieve using the hinges. It'll be fully retractable 180 degrees. Maybe you guys can use it as a stool for any other purposes. And this is our base on the side view. It's, like I mentioned, 3 legs protruding off a circular base. We're hoping to have a mechanism that'll be able to hold the cylinder. You simply push the mechanism, the cylinder will go down, it'll lock in place. Then you'll place this base on top of the actual seat. Therefore, it'll be fully compactable. And this is kind of a visual we made, sort of rough, but kind of hoping you guys can get the idea here. As the chair, when it's fully open, the arms are, like I said, not fully conceptualized yet. And we have our closed seat. We'll find a way to attach the actual base of the seat to the back of the chair.
All right, so here we have the CAD drawings that we made of this is particularly the cylinder that we have. It shows like how it's going to be retracting and extending outwards when we use it. Right now, this is just to visualize what it looks like specifically, and then this is like a rough picture of it. And here we have again just the schematics of it. It has like the measurements, which I mean, right now we're not going to go to detail about like how exactly like the specifics of the measurements, but it's just there. It's like, you know, give you more like a bigger representation of what it looks like. And here, this is the plate mechanism, which we scavenged from an office chair that we had. And then on the right is like a picture that looks like it. It's not like the exact version, but it's similar just for reference to see like what it actually looks like for us. And on the left is on the CAD drawing that we had, which is like I said, representing like the visual that we have on the right. And it's just there just to see like what it looks like and how it's gonna go. And here, once again, we have like drawings with the measurements. Yeah. And this is the base that we made. It's not finalized yet. It's just there just purposely for the just solely for the prototype right now. It looks a bit rough, but we're gonna like fix out later. It's just there for just to see like if it works or not. Right there, we have like the 3 legs that they said around the circle, and then right there's like a little hole for the
We actually have like a handmade prototype for now.
This is pretty much.
Okay, so
Stop sharing so that we can see that better.
we're trying.
There you go.
Look at that.
Yeah, so this is what we got going on for now. We're obviously going to make improvements. So right here is just a 3-prong base right here. And for now, it's very rough, like attachments, but it will eventually be like a part of it. And then this is the idea that we were having with the hinges, where it can kind of just like just sit on top here, and hopefully, like Stefan said, we'll be able to have it flat just in case, or removable in case you guys wanted to use it as a stool.
I want to note that it's very, like, this prototype, as you can see, is very rough, made out of spare parts. It won't function as we have mentioned it would, but merely it's for visual presentation.
Yeah, it's good.
I like your prototype.
Yeah.
It's a lot more functional than we see for some of them, and that's great for this time period. So, actually, I'll let Dave and Gene talk first. You guys got comments?
So guys, again, I'm impressed by the fact that you've put something together there. Now you can start tweaking this. What type of material are you considering for the cushions, the seat in the back?
We were initially planning like our basic fabrics that you'll see on your normal office chairs and some executive office chairs. Obviously, like we said, the heat resistance and the tearing is important, and comfortability. So we're thinking Kevlar, like woven fabric, or polyester.
Okay.
Some things you could.
All right, very good. I like that. So how much would you estimate this chair is going to weigh when it's done?
That's what we were trying to calculate. Roughly, from what we have seen so far from our individual parts, it'll weigh close to what an office chair will weigh on average, which is around 30 to 40 pounds. We're hoping to get it down to 20, maybe 15 at the very minimum.
Okay.
Just to keep realistic standards.
All right, gotcha.
The question I was going to bring up, the thing I was going to bring up was, you may want to watch having 3 prongs on the for the legs on below. There's a reason why most desk chairs like we're on have 5 or 6, and that is on a trifold thing like that. If you lean one of those ways, it unless those legs really splay out, it will it'll have a problem and tip. But I really do like the fact that you have those as being flat, because that ends up giving you a more surface area to rest on versus just being like wheeled or something like that. Having it almost like a ski, I think is a good idea. And I also like, and although I'm not familiar, I have to defer to Glenn on this, the piston, which of course is in all chairs. Pneumatics like that, would they be okay in a hab, Glenn?
I think they would. And so there's 2 components there, right? There's a spring that's pushing it up, and then there's the pneumatics that keep it from coming back down, because all you're doing is you're closing off the air cylinder.
Okay.
And so take a look at that. As far as I'm concerned, I don't have a reason why we wouldn't allow for that. So I think it's actually a good idea.
Okay.
I also like your idea about, it being flat and not on the wheels. I think that's also very smart.
Yeah. Yep. And one last thing, when the piston goes up for that height, which is what we wanted, you might want to definitely test for stability, because you're going to have somebody sitting on there, and whether or not if they lean, what will happen and things like that, because it's going to be a very different center of gravity. But nicely done. I really like your prototype.
Nice job.
Yeah, and I really like that it could make into a stool. Make sure it's a steady stool, but I have a stool in my kitchen. I use it all the time. For small people, that's a real important thing. And I know in the habitat, we're going to use the whole height of that habitat. So it might be quite out of reach for some of the astronauts that are going there. So that was pretty cool that you designed. I love when you design it to be more than one use. Yep. That is a great use, because I know it's a necessity in my house.
So I noticed you've got a hinge for the back, and that I think it's a good idea for it to be hinged like that. You might look and see if there's one that has a ratcheting mechanism on it, so that you can position it so that it can be at different angles for comfort reasons. But I think that you're going in a really good direction for that. One more thing, Dave brought up the materials. remember, we're also going to need it to be cleanable. If they use it for food, I don't know about you guys, my office chair has a couple of drips or whatever on it, and so being able to clean it could be really valuable. So think carefully about the materials you choose, or even things that you might add to it onto the cloth or something like that. Might make it easier for it to clean. All right.
So did you sew? Did you sew your cushions? Did you?
So
already?
for now, we kind of just stapled it together, but it will be sewn so it can look up.
Yeah.
No, and that's good. My mom used to do upholstery, and a lot of it started off with stapling as well. So that's good.
You're asking the wrong question. The question is, did you take Alvarez's dining room tablecloth? Yes, you did.
Those teachers make a lot of sacrifice for our students. I can't tell you the number of things I decimated to bring in for my students.
That's really cool. Thank you, Mrs. Alvarez. Do you have any questions for us?
Yes, a few.
So we're wondering, until we figure this portion out, would tools in the inflatable habitat, is there like a limitation to them? Because our cylinder is connected to the seat plate mechanism through pressure lock. So the only way to really get it out right now that we found is to use a pipe wrench. That's like a downside.
Yeah, the pipe wrench is what you have to have on those things. Believe me, I know.
Is that I've never taken one apart. Well, I know that the space station has a pipe wrench, and I don't want to put limitations as to what kind of tools you use. It's more about, the more tools that you have to get out, the longer it's going to take you to get it assembled. So it's really more about assembly, trying to keep it as quick and easy as possible. Does that make sense?
Yeah.
So I would expect that we're going to have a pipe wrench, but if that's the only thing that we use them for, I don't know. But so any kind of tools that you think you might need, that's fine. Just try to minimize the number of tools you need. Okay.
Any other question? We're good?
One question, is there really a need for commodities? Because we're really interested in making these chairs comfortable and look nice. So would armrests be are armrests something you guys are sort of looking for?
I kind of like the idea of having it optional.
I think that if you guys can put it as an option, I think that's terrific. I don't know. Yeah. Are you guys using your armrests right now? I mean,
yes.
I am. I think that if you can make them optional, I think it's a great idea. It's not a requirement. But yeah, I think that every astronaut I know would probably use it if it was available.
So the problem with the armrest is I have a table that my chair won't fit under if I have my armrest done. And I don't know if you can see, but my armrests go up so that I can, sit at any kind of table, not worrying about my armrests interfering with it. But I use them, but an option would be the best.
Oh, I'm checking the weight of my chair.
That's going to add weight. Every little thing you do adds weight, and it's $1.2 million a pound for the moon. So,
I want to save you guys as much as possible.
Yeah.
Yeah.
How much does your chair weigh, Glenn?
It's heavy.
Is it heavy?
Yeah.
But that adds the stability to it too.
It does.
It's a heavy.
Well, and that's part of what makes this project difficult. It's
Yeah.
It's just difficult. These are the things that we're going to have to think about. As far as I know, HUNCH students are the only ones working on this kind of project. So you guys are really kind of developing a kind of a fingerprint for what we're going to move forward with. So keep going with this, guys. I think
Yep.
you're doing a good job.
And I like you were conscious of of rounding your edges, and think about the cool aspect too. Make that seat so the astronauts want to sit in it.
No, and I'm not sure how you chose the color, other than just that it was the
Tablecloth.
The tablecloth. I think that in the long run, not on your first prototype, but I think that color is also going to be important. What kind of colors do we want to send to the moon? I don't want it looking like inside of a McDonald's. I also don't want it looking like it doesn't want to look like the wall. NASA's really good at sending up white things. So giving some ideas of color schemes might also have some value to making something valuable for the moon as well.
We'll definitely take that into consideration. Thank you.
Well, thank you so much. I appreciate that.
Now you guys are working as a whole class on this, correct?
Yep.
So why don't you show us the rest of the team here?
We like to see the team.
Excellent. There's everybody.
Everyone.
I just wanted to comment that I really appreciate the way you guys are working on this. Here at NASA, we get lots of people to work together. I mean, if we're developing a chair, we would probably we'd be depending on a team somewhere near the size of your classroom for each item that we're developing. So you're getting a good experience with this, and I like what you're doing. Keep it up, team.
Yeah, we appreciate that. All right. Thank you all so much.
Thank you.
Okay.
All right.
That's it for this month, actually. We don't meet again until December.
Okay. All right. I will talk to you all
Good
soon.
day.
Yeah, thank you so much, Dave, Jean, Glenn. I really appreciate you. Do a tremendous job, all of you. It's such a pleasure.
Thanks a lot, Marianne. We'll see you soon.
Thank you,
Yeah, we'll see
Marianne.
you. Oh, did people say that you're coming out to, because they said to me,